every object is in between pure nothing or pure being. And this is one of these dualities, and we'll see that it serves as the basis for a whole tower of such dualities.
Today, you'll discover how category theory acts as a metaphysical microscope, revealing that contemporary physics isn't too mathematical, as critics claim, but rather lacks mathematical precision at its foundation. NYU Abu Dhabi researcher Urs Schreiber mentions that the problem isn't that physics is too mathematical, rather it's not rigorous enough. Thus, precision is needed, and we have today's specific and defined talk. Building on Hegel, Urs begins with the concept of pure emptiness and unfolds through logical necessity. You'll witness the spontaneous emergence of something called the superpoint, an 11-dimensional space-time, and even supergravity, all without assuming their existence beforehand. What if the entire universe, space-time, gravity, and quantum structures emerge naturally from the most fundamental logical structures possible? Urs Schreiber. Great to see you. Thanks for coming out.
Well, thanks for inviting me. Yeah, it's a pleasure.
Why don't you give an overview as to what this talk is about and what inspired it?
All right. Yeah, what inspired it was really your invitation. I didn't really plan to give such a talk before you invited me. And then I thought, well, what would I say? And then I thought, well, the title of your podcast is Theories of Everything. So I thought, well, okay, maybe I can say something in that direction. And so essentially what I ended up doing here, what I ended up compiling and what I hope I will be able to present is a little bit of an overview of, various things I've done over the last, I guess I have to say decades now, last 20 years or something. Starting with some basics in ontology, you might say, and then maybe if we have time, arrive at some, actual experimental physics.
Yes, great. So the mathematicians in the audience would know you from nLab, which is a monumental website, and it's monumental in a few respects. So one is it's the categorification of any subject that you type in that has to do with math. It's also quick. It's also quicker than Wikipedia. I don't know why that is. It's extremely snappy, and it's a pleasure to scroll.
You mean just the pages appearing?
Yes.
Technically?
Yeah.
Oh, okay.
So tell me about the creation of nLab and what inspired that as well.
All right. Yeah. So, well, what inspired it? So underlying it is the desire or the wish to, chat about math and physics while, being productive, while making some net progress, while, whenever you figure out something, make a note about it. That was the original driving idea behind it, that there is a place where we can discuss things, but then also, that was the original motivation anyway, but then also have the opportunity to record any insights, any actual advancements that have been made. So it started out as very much, not an encyclopedia, which maybe it is what it appears as now. But I think as the introduction, the homepage says, it's meant to be lab notes that people may have flying around in there, on their desk or in their lab, where they make notes, what they have been writing on, what they have been thinking about, what they plan to do maybe, and give that all a home. And yeah, it started, that was actually back in the days before the modern version of social media. There was a time when people would discuss physics and math not on, the commercial websites that we have these days, but on what is called the Usenet, right?
Right.
Maybe some of your viewers know what the Usenet. That was the free internet version before it was taken over by companies, where we would just hang around. There was a group called Sci-Physics Research where we would discuss. And then later, when that kind of became problematic, some people switched to blogs to discuss on blogs, but that didn't really work out well. So on a blog, it's mostly just one person making declarations, saying something, and then other people can comment a bit, but it's not really a discussion. And yeah, anyway, so out of these inclinations, I started the nLab at some point, and it has been growing slowly but surely ever since.
What is it about category theory that made you take it so seriously you created an entire website about its viewpoint? So is there something different about it as a framework compared to first order logic or set theory or what? Does it subsume the rest? I know it's not merely about category theory, but please elaborate.
Yeah, so that's a very good question. So actually, I think it's this is a common misunderstanding. Not sure if I know many people think that kind of the nLab is only about category theory, and that's certainly not the case. As anybody who has ever dived a bit deeper into it, there's lots of other subjects. So to my mind, the point of category theory is the organizing principle. The category theory is like the big index of math where things find their place, find their home. So it's the organizing principle behind stuff, and as such, it's, I think, ideal for an encyclopedic, or almost encyclopedic website, because it allows to relate things in the proper way. You can go and say, oh, here's a construction in that such and such field. Oh, but look, it's just such and such limit that also appears here and here. So things get the proper context and become meaningful, I suppose. But it's also true that not so much maybe these days, but in the original years, we added just a lot of categories, just of actual category theory. I mean, what's happening with the nLab is really mostly it's growing. Nobody is being paid for editing the nLab. So what happens is people edit it when and if it's useful for them as editors. So for me personally, I rarely go and make an edit for somebody else's sake. I make an edit if and when I'm learning something or making notes for myself. So back in the days when I was learning category theory, I made lots of notes on category theory, and other people did.
Before we get to your presentation, I want to quote something from you from the Philosophy Stack Exchange. Like I mentioned, the mathematicians know about you from nLab, and maybe the philosophers are familiar with this because this is, as you'll hear. To sum up, I think the lesson is the following. Once you have a formal system that formalizes what was previously, quote-unquote, just a natural philosophy, and I should give some context to this, the questioner was asking on Stack Exchange, has philosophy contributed to anything outside philosophy in the past 20 years? And they were particularly thinking about the STEM fields. So your response was, to sum this up, I think one lesson is the following. Once you have a formal system that formalizes what was just natural philosophy, such as when Newton had his laws of motion nailed down, reasoning with that formal system will be far superior than what any philosophical mind unarmed with such tools may possibly achieve. However, these formal systems, our modern theories of mathematics and physics, don't just come to us, they need to be found, and finding them is generally a hard and non-trivial step. Once we have them, they appear beautiful and elegant and of an eternal nature. It makes us feel as if they've been around in our minds forever. But they have not, and this is the point where philosophical thinking may have a deep impact on the development of science. Expand and talk about its relevance to today's talk.
Right, yeah. So actually I was planning to end my today's presentation on such a note when we talk about maybe non-perturbative quantum field theory and maybe M theory, and how a big problem there is that it's not just hard. I will end by saying that understanding non-perturbative physics, like confined QST and strongly coupled solid state physics, is the big or the grand open question of theoretical physics of our time. And the question, or the reason why it's so hard, is that it's not just a problem that is already formulated in an existing theory where we just need to go at it and just follow the rules, and it may just be tough, but we essentially know what we have to do. No, it's because we're actually lacking some language. There's something actually missing. Some conceptual language level insight is lacking that would tell us what we're even looking for. And I think that is the reason why so little progress has been made on this subject, non-perturbative quantum field theory, because there are a few proposals, of course, but by and large, there was very little to go by. And so I will maybe try to convince, or I don't know, try to present some evidence today that, going back to some really deep-seeming ontological foundations, maybe philosophical foundations, if you will, but all in the realm of, formalized, provable math, does have something to say eventually on such open questions. And that, I think, goes very much in the direction of the quote which you just quoted, which arose actually from that post that you just quoted was made at an intermediate stage of the development that I'm going to present today. Because, there was at the time when I started appreciating this as some people have heard me say, the Hegelian aspect of parts of topos theory.
Mm-hmm.
And we were, at that time, we were like concretely interested in understanding an open question, which is what that post is referring to, namely the question of how to understand like generalized differential cohomology theories, which are, as maybe I can say a bit more later, which are meant to be the actual, full mathematical formalization of gauge fields, of higher gauge fields. And that's actually, that wasn't quite clear actually. And I, that was really what I did since my PhD thesis, just thinking about how to properly phrase the idea of generalized, meaning also higher gauge fields, like one expects to see in string theory, like RR fields, the supergravity C field, and these things. What is it really? Like, what is very fundamentally, what is it we're actually looking for when we say we want to build a model of the C field, say? And that was very much not clear. And so then we started toying with these modalities on toposes, on infinity toposes, of course. And at some point, the solution appeared. And it kind of appeared in tandem with, me at least understanding also the role of what these modalities, the role that these modalities play in more philosophical realms. So there was a back and forth. I can't really quite tell what was first and what came later. But that was the question that this blog post, this Stack Exchange post, was referring to, the question how to formulate generalized differential cohomology and hence high gauge fields in full generality and deeply. Yeah, and it turns out that it is related to this term of cohesive infinity toposes, which is something which is a term borrowed from Levin, who in turn was reading Hegel and trying very hard to understand what is actually going on there, and I would say actually succeeded, which is quite fascinating, actually.
Yes, you said that. Okay, so to be clear for the audience who hasn't read it, the question was about, has philosophy inspired anything outside of the field of philosophy in the past 20 years? And you said, yes, in differential topology, particularly with twisted cohomologies, and that's a new result within the past year or two. And then you mentioned Levin and categories of being and nothing. In particular, you said that there is a formal sense in which nothing and being can be combined to become becoming. And that's a formal, precise mathematical sense. Is that what's going to be covered in this talk?
Yeah, I have something on this. Maybe we shouldn't spend all too much time on it. One can get lost in these musings. But yes, that will appear briefly. And yeah, so I wanna kind of go back to this creation story, if you wish, and show how once notions are set up that one can speak about these things, there is a progression actually that starts literally from nothing in the technical sense of the initial object of some topos, and then progresses to discover a whole lot of physics actually, and it's at least fun. Also, I should emphasize, I'm not selling any theory or anything. I'm not going to, present any hypotheses that people need to buy into. I'm just presenting some facts, some just provable facts that are just curious to look at and that everybody can make up their own mind about, but which certainly do seem suggestive of something. Yeah, and I thought I'll take the occasion that I'm speaking here to your audience on your podcast to go back to these old ideas and do a little bit of an exposition of them, yeah.
Wonderful. All right, let's get to it.
All right, yeah, thanks. So, so as I just said, I'm going to try to give a bit of an exposition of work I've been doing over the last years, or decades even, that all revolve around a little bit of aspects of what one might call going towards a theory of everything. So these are some expositions of some theorems that you can find published in the literature. I put pointers where possible, but of course I'm trying to give a bit of an overview and some gentle introduction first. So very broadly, as this little animation that I started with here shows, is we want to start looking at something at the very foundations of thought. So this is, as we'll get to, a little cartoon of an adjunction in category theory. And by analyzing some structures that appear there, which which are sort of known to some experts, but actually not widely known, we'll see some dynamics emerge, some dynamics in the Platonic sense, in the realm of ideas, where concepts will emerge, and eventually we'll be talking about gravity, supergravity, in fact, 11-dimensional supergravity, and then maybe the M5 brane. And if time and energy is sufficient, I'm a little bit worried about energy, but then we'll get to some actual statements about strongly coupled quantum systems with what is called topological order and anionic excitations, which is what this little animated cartoon on the right is alluding to. And that connects to the actual current research I'm currently doing.
All right. And why don't you explain the title as well, please?
Right, the title of this page. Right, so I was thinking about how to call this. And, I must say there's a curious, how should one say, there's a curious aspect of 20th century science that some of the deepest thoughts have silly names. Like theories of everything is not a very elegant name. I mean, it's not too bad. The really bad ones are like Big Bang and black hole, right? So these are terms that started out as jokes. So I was thinking of a more academic sounding name for theories of everything. And pantheorias is maybe a good thing. So I thought I'll call this talk about theories of everything, but in a slightly more fancy version.
I see.
That's what the title is saying.
Okay.
It's really what it really is. So I'm not claiming, I will of course not claim to have any theory of everything in my hand, but I do want to claim that I have found some fragments of what looks like should belong to such a theory, or at least which are noteworthy to take note of if one is interested in theories of everything, in an actual deep sense, like in the sense of starting not just from the assumption of the notion of quantum field theory with its implied notion of space-time and everything, but starting deeper, like at the level of pure logic. That's maybe part of the fun aspect here that I can offer something about.
Interesting. So are you going to derive space-time from logic? Or is that a hope of yours at some point?
Yeah, so there's certainly a kind of emergence going on here, as I guess you can probably already see here from the title of this third item here. We will see that first the super point and then aspects of super space-time do emerge in some sense. I don't want to make too strong a claim here. I don't want to overclaim anything, but there is certainly something like this going on, where not just a space emerges in the sense that we already had a notion of space, and then here's a particular one, like the bulk to a certain CFT, as people like to do at this time. The actual concept of space sort of arises actually. But it's maybe hard to explain without actually explaining it. So maybe we should just
yeah, please.
I'll start with something of a hot take maybe. So just to put what follows in perspective, I'm gonna claim that what we want to be doing is, if we're thinking about theories of everything and theories of physics in general, we want to be thinking about mathematical language as a metaphysical microscope. So I have these well-known quotes here, just to appeal to authority, or just to remind us all that this thought has been important to people in the past. But I think it's being forgotten often these days, where people ponder deep paradoxes or remaining paradoxes of fundamental physics by having chats about them in ordinary language, and the debates over many such topics like interpretations of quantum mechanics or the nature of the singularity and gravity and all these things. It's easy to have long debates about it that effectively lead nowhere, because I think we're lacking, or everyday language is lacking, the terms to actually address the actual issues. And it's not meant to be surprising anymore, right? That if we speak about fundamental physics, which by its very nature is outside our realm of experience, we need a better language than just the ordinary mesoscopic everyday language in order to speak about these things. And that language is, or has to be, mathematical of some sort. So I will try to show some aspects of how math can actually help with, not just with computing quantities, but with computing, if you wish, qualities, like conceptual notions, to maybe preempt a certain debate that I know is going on in some circles. I want to maybe make the following warning. There is in the public discussion on social networks and so forth, there's this idea, this meme, that the main problem with contemporary physics, some people have this complaint, right? The main problem with contemporary physics, and especially string theory, is that it's too mathematical. That's what some people say, which is a curious thing, because in view of what our forefathers here said, and the way I perceive it, it's actually the opposite, that we're actually lacking mathematical formalizations of most of quantum field theory, certainly everything that goes beyond the standard perturbation theory, and pretty much everything in string theory. And I think the resolution of this apparent paradox, how can it be that some people complain that physics has become too mathematical, like theoretical fundamental physics has become too mathematical, and others like me are going now and say, no, wait a second, it's actually the opposite. We're lacking math. I think the trouble is that even the meaning of what it means to have mathematical formulation of physics has been forgotten a little bit at times. So what I'm speaking about is having, first of all, precise definitions, like to have definitions, exact, unambiguous definitions. That's actually more important even than the rigorous proofs that one can base on these. It's a problem with lots of ongoing current contemporary physics that it's absolutely not clear at a fundamental level what people are actually talking about, because things are not defined. And so that's what I want to mean by mathematical technology in physics, to have some precise definitions. So what people mean when they say that contemporary physics, especially string theory, is too mathematical, they really mean it's too schematic. That's really what it means. Like when people talk about rains or maybe the swampland or generalized symmetries, or all these things. It sounds very mathematical, but for the most part, it's actually absolutely not mathematical, in the sense that if you show the discussions to a mathematician, you wouldn't be able to understand anything. What it really is, it's schematic. Like, it's not filled with physical life, but it's also not filled with mathematical precision. And so it's maybe a mistake to mistake that for math. Anyway, so that's my little hot take warning at the beginning.
I think what many people, not every person, but I think what many people mean when they say that modern physics is too mathematical is particular theoretical or high energy physics, and that it becomes disjoined from experiment. Yes. And at some point you're using math that's been inspired by the math that's been inspired by, and you're exploring this mathematical space, and it's not clear that unless you're someone like Max Tegmark, who believes that the universe is mathematical and all mathematical spaces are realized somewhere, unless you believe that, then it's not clear that the realm that's being explored in much of the archive in the high energy section is of the realm of math that is joined with reality. So I think that's what's meant. As you know, on Theories of Everything, we delve into some of the most reality-spiraling concepts, from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, TOE, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe, joined with reality. So I think that's what's meant.
No, absolutely. I agree, but I was trying to add to this the following observation. You started by saying it's perceived as math because it's not related to experimental physics, right? That's what you said at the beginning. It's no longer clear how some of these discussions actually relate to experiential physics. But at the same time, I think it's actually a mistake to say, oh, if it's not physics, then it has to be math. Because on top of that, much of this discussion is actually not math in the sense that it's not precise. It's not something that...
Right, it's not as rigorous.
Yeah, it's not something that you could actually explain to a mathematician. They will not. And that's, I think, one reason why we're not seeing as much interaction between math and physics these days as maybe we did in the 90s. The mathematicians pretty much are lost. They do not know when there's this talk about all these brains and everything. They just don't have an entry point anymore. It seems like, that's why I said it's schematic. It's neither physics nor math, actually.
Interesting.
So let's see how this works. So I want to start talking a bit about category theory. At the same time, I'm actually a bit reluctant to give anything like an introduction to category theory. So I'll drop some what I think are good ways of some buzzwords of ways of what I think is good to think about category theory. And we'll see maybe if you have more questions or anybody has, if we can of course go deeper. But the main point I want to emphasize here in speaking about category theory now is with this goal in mind that I mentioned at the very beginning, that we want to move towards finding new theories of physics where even the form of the theory is not currently clear, like, non-perturbative QFT or M theory or something. So what we need in order to make some tangible progress for such matters, we need a language that can speak about concepts in a precise way, not just the math of quantity where we compute numbers, but some kind of formal system that allows us to move with precision and good insight in the realm of concepts and ideas and notions. And that's really what category theory is. It's like the conceptual backbone of mathematics. So, as I'm saying here on this slide, beyond the mathematics of quantity, there is a mathematics of, and there's a certain order to these things, of structure, duality, quality, and effects. It's interesting that the term duality appears here, which of course also plays a huge role in modern theoretical physics. The notion of duality that I'm going to introduce in a moment is not exactly congruent with what people elsewhere understand as duality, but there is a big overlap actually, so it's not disjoint either. And so I'm going to claim, without much ado here, that the language for these four aspects, structure, duality, quality, and effects, is categories in this order, adjunctions, and I'm going to speak a bit about those, modalities, and monads. So this technology, this categorical algebra, as it's sometimes called, is what Levin at some point identified with what Hegel in turn called the objective logic.
Note, I've written about Levir's theorem here on Substack. It actually went viral. It's a theorem that encompasses Gödel's incompleteness theorem, Cantor's diagonalization argument, Turing's halting problem, and even Tarski's undefinability theorem, as well as what self-reference means. Feel free to read it and subscribe to the Substack. It's CurtJaimungal.org.
Is what Levin at some point identified with what Hegel in turn called the objective logic, by which is meant that it's a logic, it's not the subjective logic of making statements about what we think we know or do not know, but it's a way of speaking about sort of the world, the Platonic world, if you will, even though Platonic is not quite the right word here, the world of ideas, that is just out there. It's objective. It's something that is out there, and we're trying to explore it. We're trying to get to the roots of reality, in a sense. That's what this term means. Okay, so here's a lightning crash course on what categories are about. Yeah, you should stop me maybe if this gets too boring.
No, this is great. Never feel like you're getting too technical on this podcast, because this podcast is known for not skimping on the technicalities, and the audience loves and they crave the technicalities.
All right, okay. So let me give here a couple of ways of how to think of categories. So at some technical level, but that's maybe the most boring level, of course, categories are like directed graphs, but equipped with the notion of how to compose the edges of the graph, such that the composition is, satisfies the expected properties. It's associative and unital. And then just in order to have more jargon, one calls the vertices in these graphs objects and the edges morphisms. And these terms come from what you might call the archetypical examples of categories. So as physicists, what you want to be thinking of, there are many uses of category theory in physics. But the primordial one, I think, that you should all be thinking of is categories whose objects are spaces of sorts, physical spaces, but also more abstract spaces like moduli spaces, classifying spaces. Space, quite generally, and where the edges on these graphs, the maps, as I call them, morphisms, are just maps between these spaces. And this is actually going to be a big theme in just a moment, that even though it's maybe not often fully recognized, but in order to do physics, one, like just Lagrangian ordinary classical field theory, one very quickly runs into the issue that one is dealing with spaces that are actually more general than what the standard textbooks allow for. Like already, if you're just doing like scalar bosonic ordinary classical field theory, if your base spacetime is not compact, then the space of fields is just not a manifold. It's just not a smooth manifold, because it's not. If the base is not compact, it's no longer Fréchet. So you're outside the realm of what traditional differential geometry actually offers, and not all, but parts of the difficulties that afflict field theory result from the fact that one is dealing with these generalized spaces. And if the moment you add fermions to your classical field theory, the spaces become actually superspaces, even if there's no supersymmetry. Just because there's fermionic coordinates there's a Pauli exclusion principle that says that suddenly we're dealing with spaces, some of whose coordinate functions actually square to zero, which is, of course, nothing that ever happens on an ordinary manifold. And so again, we're out of the realm of what the traditional textbooks offer us. And I think a very good entry point to category theories, and I'll get to that, to the actual examples, is think of categories as providing the context where the actual spaces that physics actually needs live, and where we know how to map between them. So what it is, for instance, for what it means to have a curve in the space of fields, on the space of superfields, on the orbifolded space of superfields, and all these things. And so the standard way of drawing these things is with these diagrams shown on the right here. So the X, Y, Z are these objects in some category, or think of spaces of sorts, and the arrows are the maps between them, the morphisms. And for any composable pair of such, we have the corresponding composite. So that's a cartoon picture here of a category, where I'm omitting, of course, what most textbooks will amplify much more is the fact that this composition operation is supposed to be associative and unital. So there is identity, morphisms on all these objects, and so forth. Another actually very useful point or like default point of view on categories is the second or third item that I'm showing here, which is not actually, as it turns out, disjoint from the previous one, is that you think of the objects as being data types. Think of this as a procedural declaration in the theory of computing and programming, where the objects are kind of data types consisting of all data of a certain type, and the maps between them are programs that take one to the other. So if we have enough time, we may get at the end to the aspect where we talk about maybe quantum programming language that emerges here, and it's in that context that this perspective is the dominant one. But these perspectives are not mutually exclusive. Like a space is the data type of the data that is a point in that space, or more generally, any figure in that space. Yeah, okay, we'll get to this. And then for those, since just to connect maybe to some currently fashionable verbiage, among categories is groupoids, where all the maps are invertible. So a groupoid is a generalized symmetry. It's a bunch of objects, a bunch of things that are not just sitting there as they are in a set, but that are connected by what you should think of as gauge transformations. So when these maps here are invertible, when they have inverses, then they identify these two objects with each other in a specific way. One calls them isomorphisms, of course. And in particular, an object can be identified with itself in several ways. Such a morphism can go from an object to itself, and that is just the operation of a symmetry group on that object. And so the special case of categories where all morphisms are invertible are groupoids, and they should very much be thought of as being the incarnation of the idea of symmetry, and specifically of gauge symmetry. You should think of groupoids, I can think of groupoids as being like sets equipped with gauge transformations. In fact, a very important example of a category is, for instance, the groupoid of, say, Maxwell gauge fields on a given space-time. So the objects in that case are gauge field configurations, and morphisms are literal gauge transformations between these. And so if from that perspective we lift this condition that all morphisms be invertible, then we have pretty much what these days people want to understand under non-invertible symmetries, namely a situation where there's operations between things that behave a whole lot like you would a symmetry. You would like a symmetry to behave, except that they are not actually invertible, and that's what's captured by these morphisms here. So I think if you go and make anything about non-invertible symmetries precise, you will in the end have to be talking about categories. And then, of course, so this is what is shown here. Then, of course, once you have these categories, you want to talk about finding images, and we'll see concrete examples of this in just a moment to give some life to this. But let me just say it in the abstract right now. So, of course, if you have two categories, C and D, you want to say what's an image of that category in that category. Well, it's just a map that from C to D that maps all the objects and all the morphisms from C to D, such that the structure is preserved. The only structure we have here is the composition of these morphisms. So such a functor indicated here by this assignment, such a functor f, takes every object to another object in another category, such that it does not matter whether we first send morphisms over one by one here and then compose them, or send over the composite. Given somehow that we have this extra structure of the morphisms here, that we're in a sense one homotopical step higher than in the realm of sets, means that such functors in turn are objects of some category. They have relations between them. In particular, they have symmetries between them. There can be something called natural isomorphisms between these functors themselves, and they can be non-invertible again. And that's what's called natural transformations. So what I'm showing here is one functor f, and here's its image, another functor g, and here's its image. And then we can ask, are these two images deformable into each other? Where, if you maybe think of, as you can, for special situations where we're looking at the categories that are the fundamental groupoids of spaces, if you think of these objects here as points in a space, and of these morphisms as actual paths in a space, then in topology it's well known the notion of a homotopy between two maps, where we continuously deform a path here to a path here, and this path here to this path here, such that the composition of these paths is respected. And now we just abstract from that situation, if you will. We don't have actual paths here. We just have these formal maps. And we can still ask, well, let this object be transformed to another object. So let there be a non-invertible symmetry, if you will. Let there be some morphism here that transforms these objects into each other. And then we want to say, well, this result down here counts as a deformation of this result up here by these deformations, if this is compatible. So, namely, if these squares commute. So there's something actually I'm not showing on this slide. This is the standard, the default understanding that whenever we draw composable arrows in different ways that go from the same object to the same object here, that we understand that we mean that the square is actually filled by inequality. So that we mean that the composite of this morphism with this morphism equals the composite of this morphism with this morphism. All this happening in the category D. So that's understood here. I will not, some people write a little symbol here. I will not do that.
Yes.
All squares commute. And later on, of course, they will not commute. There will be some further homotopies in there. But for the moment, they will just commute. So that's the basic. That's the thing. You open Wikipedia, any other book, any of many books on category theory, they will tell you that this is what a category is. And then I think at some point what happens is that for some, there's always a little bit of debate. Do we even need to care about this? Is this actually worth our time? This is trivial. If this appears trivial and tautological, then that's good. That's what it is. This is not doing much. And I now want to make another hot take. I will actually oppose now, an often quoted saying in category theory, and will want to highlight that it's not actually true. So this may originate with this reference here for F right, where which is certainly historically somewhat accurate, where people said, well, so what are we trying to do here? And there's this saying that goes, we just introduced categories here in order to speak about the functors. But why did we introduce the functors? Well, actually, we wanted to understand what are natural transformations. So the saying goes that the whole point of the setup is here to speak about natural transformations. And that is certainly the case to at least half the extent for the original article by Eilenberg-MacLane on category theory, where they actually asked what is a dual object. So they essentially observed that at that time in algebraic topology, people would speak about certain things being naturally isomorphic to each other or naturally transformed into each other without there being an actual definition of what it actually means to be natural, right? So this goes maybe back to our original discussion of speaking in an informal, non-mathematical language for things that should have a formal definition. And part of the motivation, at least, was of Eilenberg-MacLane was to make precise what it actually means for two things to transform into each other in a natural way. And the definition they came up with is exactly what I just said, the commutativity of these things. So the transformation is the fact that this functor goes to this functor, and its naturality means that we have these non-invertible symmetries coherently relating these two things. So sometimes people say, okay, so category theory is just all about these maybe categories, functors, and natural transformations. And then it does look a little bit, what's the right word? A little bit thin, right? Then we're just really looking at graphs with some composition. We can do some images. We can call certain things categories. But if we don't, we haven't really lost too much, because after all, I mean, this is nice here, but you could probably get along without maybe making a big deal and giving everything here a name.
Wait, I don't understand why you call it thin.
Well,
what do you mean?
No, I want to make a point now that there is more to category theory, a whole lot more. Like the actual theory. Well, good. Thanks for interjecting. I want to make a point here that something deep happens now in the next step. Actually, this is just the bare bones substrate on which category theory builds. The actual theory only happens in the next step. So this is this little progression that I'm indicating here. So what I've shown so far is the hierarchy of categories, functors, and natural transformations. And that, in a sense, that defines everything that is about categories. But the actual theory, the category theory, the non-trivial aspects of it, also I would say the dynamical aspect, the surprising aspect, where the real meat is, where stuff is happening, where difficult proofs have to be proven, is in the next step, where we introduce adjunctions, and out of this grow then the universal constructions that will help us let some physics emerge, and also monadic algebra that plays another role, which maybe we should talk about at another time. So I want to emphasize that beyond categories, functors, and natural transformations, there's a next ingredient in category theory, and that is, in a sense, that is the important one. That is the notion of adjunction. Of course, people will have heard this, but this is really where something not completely obvious happens, and all the deep parts of category theory are all related to adjunctions. So what is an adjunction? An adjunction is a pair of functors, L and R, going between categories back and forth. So one goes from C to category D, the other one goes the other way around, called L and R for the left and the right adjoint, and that makes them being adjoint. They are equipped with natural transformations. Remember, that was these deformations of functors from. So, right, these two functors, they go back and forth. So as we compose them, they give an end of functor on one of these categories or on the other. And so we want a natural transformation that deforms, if you wish, our composite going back and forth to or from the identity functor, the one that just sends everything to itself. And moreover, so I'll show an example of this in a moment, like a physical example of this. Let's maybe just try to digest this. So we have these things going back and forth, and they satisfy identities. And these identities are usually shown with a diagram drawn slightly differently than what I'm doing here. So I thought it would be fun, since I'm going to claim that adjunctions capture the intuitive notion of the philosophical notion of dualities. I draw what's usually called the triangle identities.
Suggestively, yes, I see.
Yeah, I draw it suggestively like this. So what this is showing is, I'm not showing the identity morphism. So there's an identity functor here from C to C, which, since it's the identity, I can just as well not show. And then we have L first, followed by R. So this is this. And what this is showing is that we have a natural transformation from this identity, which I'm not showing here, to this composite.
Mm-hmm.
And the co-unit, as it's called, this other transformation goes conversely from R followed by L to this identity here on D. It goes in this direction. So usually these diagrams are shown by expanding out these identity morphisms here to have some finite width. And then they look like, I don't know, like a poached egg or something.
Okay.
But I just want to amplify. It's the very same diagram that I'm not changing anything here. This is just the definition of unit and co-unit in an adjunction. And the zigzag identities, if you draw them this way, have this fun yin-yang form, where we claim that the composite of these transformations here has to be the identity on the L functor, and the converse composite of these transformations have to be the identity here. So that is one way of abstractly defining what an adjunction is. And one can already see maybe that the definition of adjunction is somehow on a different level than these previous definitions. I mean, here, right, we had some, it looked like, if you think of these as graphs, we're basically dealing with discrete spaces, or something that looks like discrete spaces at least, and they're images in each other. It looks a bit like discrete topology. But here, this is something that you would not maybe have guessed if you're just thinking about topology. So there's something important and deep going on here. And I'll just mention some examples. This is maybe an exercise that everybody needs to do by themselves. But let me just mention some. So I want to claim that the notion of adjunction, and that's not my original claim. This has been amplified by some people before, is that adjunction really captures a whole lot of what is intuitively the notion of duality. And as a very simple example, one can make the following exercise. One can think of the natural numbers. The natural numbers as a category, where each number is an object of the category, and where the relation that one number is smaller than another number is a morphism. So where a morphism goes from one number to another, if and only if the previous one is smaller than the other. That's the so-called, the partial order on the natural, or on the integers regarded as a category. And it's a fun exercise to see that if one now looks at just the even numbers and just the odd numbers, they have functors into the full set of integers, the full category of integers, just by the embedding. And these functors have adjoints. And so there's an endofunctor on the integers that projects every number to its closest smaller even number, or its closest larger odd number. And these two functors are adjoined to each other. They dual to each other, expressing in a nice way what you would intuitively think should be a very simple form of duality between even and odd. Uh-huh. And actually, that example, if one actually works it out, that example is kind of nice in that it shows both how being even is in some sense opposite to being odd, and at the same time, there's a certain unification going on, because of course, just as a set, or just as a category, the even numbers are of course isomorphic to the odd numbers, the isomorphism being at 1. So there's a whole lot, or how should one say, surprisingly, this baby as this example is, it has some nice philosophical insights to share. So we could look more into this, but I just want to mention this. And then there's a primordial example that will drive our emergence story in just a moment. It's in a category where there's an initial object and a terminal object, and the functors that are constant on these objects are adjoined to each other. So an initial object, and this will be our model for the emptiness or the nothingness, is an object in a category such that it has a unique morphism to any other object. To be thought of as the characteristic property that the empty set has in the category of sets. There's a unique function of sets, a map of sets from the empty set to any other set. Namely, it's the one that takes the non-existing, that takes no element to nowhere. And yes. Similarly, there's a unique function from any set to the singleton set, the set with a single element. It takes necessarily every element to that single element. And from that, you can already see there's actually a simple example of an adjunction going on here, where the unit and the co-unit maps are these unique morphisms from the initial and to the terminal object.
So terminologically, people can understand that the initial may have an analogy to something empty, but then terminal usually sounds like something at the end, which would be the highest, like the highest form of infinity. But terminal in this analogy is actually the unit set, the set with one element.
Yeah. So the terminology is, I guess motivated from partially ordered sets. If you have a set with an order relation, and you think of the relation, one element being smaller, say, than the other is being a morphism, then the initial object is what's sometimes also called the bottom element of this order set, the smallest one, and the terminal one is the top one, the top element where everything converges to. In this sense, it's terminal in that somehow every string of composable morphisms ends there. I think that's why it's called terminal. But yeah, you could maybe find different words for these. And then, so just as a side remark, I want to actually mention here, not sure if we actually get to this, but I want to mention that since I'm claiming that adjunctions are actually dualities, that you should think of them as being the mathematical formalization of the intuitive and or philosophical notion of duality, that at least some of the stringy dualities in string theory, which of course is a term that has a completely different history to it, and it's not used very systematically always, but some of them are actually just plain examples of adjunctions. And among them is, and I'm quite fond of that example, is the notion of what's called double-dimensional reduction, where you have some branes and their charges in some high-dimensional space-time, and you want to say that there's an equivalence, that you can equivalently regard the system from the point of view of a lower-dimensional space-time, where some of the degrees of freedom that you had in higher dimensions are incarnated as so-called Kaluza-Klein modes. So that's a very important and basic, kind of duality in string theory. And that is actually an example of an adjunction. Well, it's an example of a higher adjunction, higher categories, but it follows exactly the same pattern. And in particular, especially examples of this, one finds T-duality, or at least the what's known topological T-duality. And in fact, the duality between M and 2A, so the reduction of 11D supergravity to 10D. And so I'm giving some references here. There's a deep and detailed story to that. I don't want to get into this right now. If we have time, we can, of course, get into this. But I just wanted to make this a side remark to indicate that besides these baby toy examples that I'm mentioning here, there's really deep adjunctions. Of course, there's many more examples of adjunctions, but this is one that I think is, for physics-inclined audiences, immediately recognizable as something important.
Cool.
Now let's get our hands dirty, or how should we say? Let's see this in a bit more tangible form. I'm going to be talking about toposes now a little bit, and so I'm giving a specific, how should one say, class of categories. I'm highlighting a specific example of categories that is, I would argue, actually maybe the first one that any aspiring, physicist who wonders if he or she should learn category theory should think about. It's not actually highlighted very much in the literature. You will not, besides maybe our writings, you will not find this currently being amplified too much. But I claim that this is actually the golden road to understanding, to get to the heart of the matter here. So this goes back to what I announced at the beginning, the role of categories as helping to come to grips with the generalized spaces that play a role in physics. And I want to be looking now concretely as categories of such generalized spaces. And how do we think of them? Well, being physicists, if we are physicists, so there's a surprising story in physics where, in physics and math, and the physics and math histories, where physicists go and write down what looks like naive computations in local coordinates without worrying or thinking about what this would actually mean globally. A very good example is supersymmetry. You just go and say, well, what if my coordinate functions do not commute? What if they pick up a sign? And then just run with this. So in physics, you just do something that can algebraically be done on a coordinate chart. Or you say something like, which is maybe even older, you say, oh, let epsilon be a quantity that is so small that if you square it, it becomes 0. I remember actually, this is when I studied physics, we had an experimental professor who actually explained to us the volume formula for the sphere in just this way. Just assume there's an epsilon that is so small that you can square to 0. And so these are algebraic tricks that you can do in coordinates, right? Coordinates square to 0, and or they intercommute with each other, or they do other funny things, which you can easily do in coordinates. And physicists have to very good avail have used this fact without thinking about what it means, usually, what it means actually globally for a space if its coordinates behave this way. And so here, category theory actually comes to the rescue, and in its guise as topos theory, provides actually a fascinating, accurate characterization of what is going on. So it's a way to kind of bootstrap generalized, globally defined, hence non-perturbative, as people say in a moment, spaces from just declaring what happens on coordinate charts. Okay, so enough of an introduction. Let's just look at it. Suppose you have a category of what I'm going to call generalized charts. So we'll look at some examples in a moment. So these C's here could just be like ordinary Cartesian spaces, Rn's, for any n. So just the actual original Cartesian coordinate charts of anything. And maps between them, say, any smooth maps between Rn's. Or they could be super Cartesian spaces with some super coordinates attached to them. But we think of these C's as being kind of super simple, super naive things that we can handle algebraically, maybe. We could even say, and we'll see this in a moment, that C may have some nilpotent coordinates. Well, write some epsilons that square to 0. What will we mean by this? Well, we will just we'll kind of define such a C to be its algebra of functions. And we just declare that the algebra of functions is not just an actual algebra of functions, but some other algebra that has nilpotent elements. And then we just declare that these maps between them are actually maps going the other way around, pullback morphisms of algebras. So this realm is the kind of naive setup of easy algebraic manipulations on simple objects that look like little contractible coordinate charts, maybe with some extra bells and whistles. And now we want to do kind of a bootstrap from that. We want to say, okay, if these are our generalized charts, what is the most general space that I can kind of build from these charts, or that I can understand from these charts? So what is the global geometry that is kind of modeled on these charts? And the simple idea is the following. It's a fun bootstrap exercise. So we say, suppose we had boldface X that is supposed to be my generalized space. And I don't have it actually yet. So we're bootstrapping it into existence. But we say, well, if we had it, or once we have it, well, we will be able to ask, what are the ways of plotting our charts in X? That's kind of the name of the game, that we want to say X is a space that is somehow modeled on the geometry embodied by the C's. So there must be some way of mapping C's into the charts into X.
Okay, so X is something that's unknown, but you want to know it. How do you know it? You take something you do know and you probe it with it.
Exactly, yeah. Exactly. So it's a very physics operational kind of definition. We say, how do we actually understand space? Well, we understand it by throwing stuff into it like light rays and see what happens. So we probe it. In fact, it's very similar also, or very related to the terminology of what's called probe brains in string theory, where you say, well, here's some stringy background, and in order to understand what's actually going on there, well, let's suppose we have a little brain, so a little C, a little simple thing that traces out some trajectory inside, and let's study these trajectories. That's really the idea here.
It's not only physics, it's just in everyday life. You don't know something, you go out, you touch it, or you look at it, and that's how you come to know it, or know more about it.
Yeah, absolutely, right. So it should be a very intuitively obvious thing to do, and that's what we're doing here.
Even us, when we're speaking, just with human communication, you don't know someone else, so you probe them, you ask them questions, and they come back to you with something.
Right, exactly, yeah.
You can probe them in other ways, but that's for another podcast.
There you go. Yeah. Very good. Exactly. That's true. And in fact, it's very good that you're saying this. In fact, the notion that I'm that I'm exposing here is really, it's going to be the notion of a sheaf. It's so general that, of course, many other concepts will fit on it that are not manifestly generalized spaces for physics, as I'm presenting it here, which is just the angle I'm taking here. Indeed, you can, and it is being used for all kinds of things. More generally, one could say, if you have any small category, then the pre-sheaves on it are the things. It's the category of things that can be probed by these objects in the small category.
Cool.
Okay, very good. So why is it a bootstrap, though? So what the quotation marks? So the idea is now that we say we have this functor. I didn't actually write this, I see now, which goes from the category of charts to the category of sets. So it assigns to every chart, every generalized chart, a set. Just a plain set, which we think of it as being the plots. I call them plots. It's a technical term in this business. So we think of them as being the maps, the would-be maps from C into X, only that this hasn't actually been defined yet. So it's kind of, that's why I'm calling it a bootstrap. It's defined hereby, and we kind of need to make sense of it. So a priori, it's just any set which we're thinking of as being the set of maps from C to X, of admissible maps. Like this would be the smooth maps or the supergeometric maps, whatever structure is encoded in our charts. Okay, so we have these sets, and that alone can't really be sufficient to understand our space. But now, if we also know like how these sets change as we actually move around the charts, so as we actually do more of an actual probe, we don't just have one of our charts sitting there, but we move it a little bit. Like we have a map here, so this might be a smooth map between RNs or supergeometric maps between super-Cartesian spaces, or something like this.
And those aren't to be interpreted as coordinate transformations?
Yeah, you can. The thing is, I'm not requiring the map here to be an isomorphism. So it can actually, it doesn't have to be an invertible coordinate transformation. It can be, but it can just be any smooth function, actually. We're allowing. That's why I'm calling them also generalized charts. I'm not at this point actually requiring, I'm not speaking of manifolds that are defined to be locally isomorphic to one of the charts. I'm defining something more relaxed, and in fact, the whole point is that we get something that is more general than manifolds. It subsumes manifolds, but it is more general, where we just speak about not having just charts that are isomorphisms onto the image, but just any maps. That's why they're called plots. Any maps from the chart into the space.
If that's what is called a plot, then why don't you define, why is that an equality sign and not an equivalent sign, like with three vertical lines? Why is it
here? Why do I have quotation marks here?
No, right there. So why is that not a definition?
Well, the thing is, that's why I'm calling it bootstrap. It will be a truth. It will be true in just a moment. But right now, you see C and X do not actually live yet in the same category because X hasn't even been constructed yet. Or, X starts out, we're kind of defining X as being this functor, this assignment it's the assignment from any C to a set. And as such, we don't really know yet what it would actually mean to map C into X, because C and X are currently conceptually on different footing. Right? C is something we have in our hands, some Rn, and X for a moment is just a rule to take any C to a set, right?
Yes.
So right now, we don't know yet what it would actually mean to have this arrow here, and that's why it's quotation marks, and that's why we can't quite say it, that it's actually equal, because we don't even know what this is yet. But in just a moment, it will all fall into place, and we'll just remove the quotation marks. And that statement that we can remove the quotation marks, that incidentally is the Yoneda lemma, which is of course one of the is the emblematic lemma of category theory, and that will make this work. Okay, so so this is actually fun. So let's think about this. So we're going to now say, well, if I have another chart, then my rule, since I assume I have X, so if I have X, well, I will be able to probe it also with C prime. But then, if we think of these sets of plots as being such maps, even though they are not yet, but if we think of them, well then, given any map of charts going upwards here in my diagram, then we will get a map from plots going downwards, as indicated here, right? Given F, I can use F in order to take any plot of probe form C to a plot of probe form C prime precomposing it, right? So again, this is a
pullback
square, so we regard it as a commuting diagram. So phi prime here is the image of composing phi with f. So this is pullback of functions. So this just says that if you have any map of charts, you can pull back the corresponding plots. And that's right. So we want this to be true. This is the image we want to realize. And so here we're declaring it should be true. There should be a function. This was just an abstract set. There should be a function of sets, taking every element here to some element here, to be thought of as this pulled back plot. Okay? And then we require this really to be a functor. So we just require this assignment is respects to the composition. So if I have two, I haven't drawn this here. If I have two maps between the charts and I pull back consecutively, that should be the same thing as pulling back along their composite. So that's just the basics of composing maps. And there should be identity maps here on the Cs, and pulling back along an identity map should be an identity. So that's some very basic consistency conditions on our bootstrapped X, right? To say, well, if I have such a functor, I have a good chance that I actually know X. So what I'm showing here, that is called, of course, the technical term for this is a pre-sheaf, that we say it's just technical jargon. That we say such an assignment of sets, of probes, of plots to any element, to every object in a given category. Such a functorial assignment is called a pre-sheaf. If it's contravariant, like if arrows going this way turn into arrows going this way, then it's called a pre-sheaf of sets. I'm actually going to call it a sheaf. I don't know. At this point, I didn't really mean to spend too much time on it, but let me just say it in words. I don't have a graphics for that. Not right here. We could jump to it somewhere. Is that there's one more condition that we want to impose here. It's a locality condition. Let me just say it in words. Namely, we want to say, well, to probe X, it should be sufficient to use small probes. Meaning, suppose you have a C here. Think of an Rn. Say in R2, in R2. So you're mapping some surface into your would-be space. But now suppose you have covered this surface. You have formed an open cover. You've covered it by other copies of R2. So covered. So we have like little balls on that surface, and we're covering it thereby. Well, if we know where all these little surfaces, how they go to X, and if we know that their restriction to the intersections agree, so we have a bunch of probes of our space by little disks or by little RNs, such that on the intersections of these RNs, these probes coincide. Well, then we want to be able to say, well, then that's just as well as having mapped our whole surface into X, right? We know all of these little patches of it, where they go. And the requirement that this is the case, so first of all, that one has a notion of what it means to cover coordinate charts by other coordinate charts. That information is called a coverage that makes this category what's called a site. And then the requirement that our functor of plots respects this notion of gluing, that is called the sheaf condition. And a functor that satisfies this is then called a sheaf.
Okay, so let me see if I got this correct. So you were saying that physicists ordinarily live in charts, and the chart is the mathematician's way of speaking about coordinates. And then differential geometers know this, and that's why they work coordinate-free. Now, you're saying, okay, well, the differential geometer's way is you first define a manifold, and then you start to define charts. So you go from the manifold down to charts. But you're saying, well, what if you don't want your spaces to just be restricted to manifolds? What if you want to generalize even differential geometry to different geometries or different spaces?
Yes.
Then that is what's called a gross topos.
Yes.
And you do so actually in the opposite way. Instead of you first define your object and define the maps from your object to charts, you're doing it the other way. You're saying, okay, well, we have to start from what we know and then probe upward.
Yes.
Of course, with compatibility on the overlap, and that's referred to as gluing.
Yeah, I think that's a good way of thinking about it. I might just add that, of course, secretly, even in the standard textbooks on manifolds, secretly, of course, you need to know what Rn and smooth maps between Rn are before you can go further. That's something you know at the beginning. But it's of course true, as you said, that a big emphasis is put these days on the global spaces, the manifolds, in favor of the charts. But But that can only be done after the definition of manifold has been made, which very much relies, of course, on the notion of charge, right? And so that's what's going on here too. We want to say, what are these global spaces, boldface X? And we need to say that in some way or other, they're actually determined by charge. That also for an ordinary definition of manifold, the actual notion of what is a smooth function between charges, that actually determines what is a smooth function between manifolds more generally.
Got it.
So we want to say a generalized space modeled on these charges is such a sheaf, such a contravariant functor with such a consistent assignment of plots. And now, actually, of course, now that we're talking categories, we also want to make the collection of all these generalized spaces a category. So next, I want to say, what is a map between the generalized spaces in turn, right? What if I have X and Y? And let's go there. And what is a map from X to Y? And a quick way of saying this is that since X and Y were defined as being pre-sheaves, then a map between them is not just a natural transformation between the corresponding functors. But let's see that this abstract idea, again, has a very concrete and very satisfactory incarnation or realization for our intuitive picture of spaces probed by charts. So we want to say, what is a map between these generalized spaces from boldface X to boldface Y, called boldface F now? Well, the idea is to again pretty much as one does for manifolds, to reduce it again to what happens on charts. So in order to know what this map does, well, we remember that our plots from charts were meant to be like maps into the space X. So suppose I have a C here, a chart mapping into X. Then if this is really a map of these spaces that preserves, all the given smooth, whatever, supergeometric structure, well, then it should be possible to compose these maps, phi followed by F. And that will give us a generalized chart of Y, right? Because now this map from C to X has been pushed forward to a map from C to Y. And so that is what we make the definition of F, a map of, since our spaces were defined, bootstrapped by saying what their plots are, we say a map between these spaces is whatever takes plots to plots consistently by a would-be operation of postcomposition. And so the requirement that you have this for all C, compatible again with the maps between the chart C, is what makes this a natural transformation between these functors by the rules that we introduced before. And so this gives us a category of generalized spaces modeled on any category of charts. And that such a category is called, that's the jargon, that's called a topos, or actually a growth topos of generalized spaces, which is the sheaf topos, as people would say, on the side of charts. So that's just jargon for exactly what I just said.
Okay.
And sort of my running claim here is that even if you will rarely see, I mean, I have some references here, but even if you will rarely see like spaces for physics be explained this way, it's kind of in the background. This is what one can see is happening when people actually handle generalized spaces. And I want to amplify here that this idea, this is ancient actually. This was promoted by Grothendieck way back in 1965, when he actually started saying that this is the way to do algebraic geometry. Instead of talking about locally ringed spaces, one should regard schemes and more general algebraic spaces as being just such assignments, where now C is not a category of smooth charts like it is for the applications that I have in mind here, but a category of affine schemes, right, of formal duals of rings, algebras. So it's an old idea, but somehow I had a quote which I didn't dig out now. But there's some quote, like many years later, Grothendieck writes something where he's frustrated that people are still talking about locally ringed spaces instead of using this. Just to amplify, this is also a very good example of how the language of categories is actually useful, even in its basic form. Remember, we haven't talked about adjunctions here at this point yet, so we're really just in this lower stage of categories, functors, and natural transformations. We used exactly that to do something useful that is simple, but actually it already makes this terminology worthwhile, just to say what a generalized space is. So here's the statement about the Yoneda lemma, which I mentioned before. One can now ask the following, right? And so this now gets us to the question with the quotation marks here. So here's an example. I should give an example of what is a generalized space. And the default example is, well, the charts themselves are generalized spaces. Well, how so? Well, we need to say what are the plots of an actual chart. Well, we just take them to be the actual maps, right? We want the plots to be like maps, but now if the space C is a chart, well, then we can just use the maps because we had already assumed that we know them, right? That was our starting point. They had a category of charts. So we can regard any chart, generalized chart, as a generalized space by declaring its plots to be just the actual homomorphisms of plots into it, of charts into it. So then there is a priori a little chance for inconsistency here, because now C now suddenly exists in two guises. It exists as our original charts, which entered the definition of plot C, and now it also exists as a generalized space. So there's now these two things that a priori could be different. There's the plots of C as just defined, the bootstrapped, if you will, declaration of what should be the admissible maps from any chart into RC. But since we just built a category of generalized spaces and made C a generalized space, we can also map into C
right
as a generalized space, right? And a priori, at first sight, it's not actually so obvious, maybe, or at least it's not completely self-evident right away that these things are actually the same. But they are the same. There's a natural isomorphism between these two functors. And that is the statement of the Yoneda lemma, which is maybe a fun thing to notice. Everybody has heard of the Yoneda lemma and how it gets mentioned all the time in category theory. And here we see that if you think of categories as being categories of generalized spaces for physics, then the Yoneda lemma plays this very crucial, pivotal role here as saying that's actually consistent. That functorial generalized geometry for physics is actually consistent. So that's a fun fact maybe to notice. Now let's get to some actual examples.
Cool.
So this is from this encyclopedia article that I have on Toposes theory in physics, just copied verbatim.
Oh, I love this. I watched a talk of yours, I believe it was at the Wolfram Institute, or it was on higher topos theory.
Yes.
From a few years ago.
Yeah.
So I love this part.
Okay, very good. Yeah, actually, in fact, that was January of last year. I was visiting in Beijing at Tsinghua University. I was giving the talk there, but it was remote to the Wolfram, whatever it's called, Wolfram School. Yeah. Right. So, here's I want to say now, what are the charts that we actually use in physics for the most part? Like when we're talking about field theories okay. I mean, let's go through this. So let's look at what these charts can be. I already mentioned this most emblematic version, maybe just the Cartesian space, the original notion of a chart, and the indices here they run, right. So I'm not writing for all. So if I write Rn here, I'm thinking of this. It could be an Rn or an Rm, for any natural number n here. So we're looking at any Cartesian space here. Just to repeat, since we're not currently requiring anything to be locally isomorphic to our charts, so we just probe by all possible things we have. And so probing with Cartesian spaces, the kind of geometry that this models might be called differential topology. We're talking about spaces that are not necessarily manifolds, but that have enough smooth structure of source that we can probe them by Rn's. And in physics terms, maybe I should say more about this, but let me just say it the way it says here right now. In physics terms, that is the setup which allows us to speak about fields in the sense that in the sheaf topos over the category of Cartesian spaces, the mapping spaces from, say, space-time to any coefficient space, say the complex numbers or some Lie algebra, these mapping spaces, which in general are not manifolds anymore because they're too highly dimensional, they just exist.
I should say that this is like the basis of all of physics, all of modern physics on a business card.
Yeah.
Now, it's not the standard model, but I mean, it's the language that underlies modern physics.
That's right, yes. That's right, yeah. Exactly.
So I like this. It's quite impressive.
Exactly, yeah. That's Yeah, exactly. That's the substrate on which things are built. Yeah. This stage is actually not as famous as this one, but it logically comes before it in some sense. I'm using the symbol little d here, which is for disk. So you should think of these things as being infinitesimal disks, like sometimes people say halos. These are like points in an Rn with just an infinitesimal neighborhood of a point in Rn around them. And the infinitesimal neighborhood is of order k. That's why this has two indices. So dn means, think of a small disk in Rn, and the k means it's so tiny that the k plus first power of any function on that disk actually vanishes. The disk is so small, right, that its coordinate functions, if you take them to the k plus first power, don't just become smaller, as small numbers, smaller than 1, tend to do, but actually vanishes.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.
But actually vanishes.
So the experimental physicist that was your teacher would have k equals 1 in his example from before?
Yes.
Of squaring to 0?
Yes, that would be the first order infinitesimal disk, yes. Exactly, yeah. You can also see in the original Feynman articles, I think in his thesis where he introduced the pathing, that he is also playing with such epsilons. And this is a fun story because physicists must have been using this even long before Feynman, I suppose, probably for 400 years or something. This kind of trick, and it took mathematicians quite a while to fully come to grips with this. But it's exactly in this way. This goes now by the name synthetic differential geometry, where one considers sheaf toposes on such probes or similar with infinitesimals, and then notices that inside these sheaf toposes, one has, that's why it's called synthetic. Inside these sheaf toposes, there's generalized the infinitesimal disk then exists as an actual object and all other kinds of infinitesimals. So that one can, for instance, go and define inside these toposes, define a tangent vector to any point to literally be a map from the infinitesimal interval into the manifold, such that the foot point of the interval goes to that point. So it becomes literally an tangent vector becomes literally an infinitesimal path in the manifold. That's why it's called synthetic, because the usual heuristics of what differential geometry is about kind of becomes a synthetic reality. It becomes synthesized to something that actually exists. And for physics application, this means this is really where calculus of variations takes place. In particular, so this is a bit technical, but in such a synthetic differential topos, so once you have such charts among your generalized charts, you can very naturally speak about jet bundles and differential operators and Euler-Lagrange equations, because all of these, like all of classical variational field theory, is all about kind of doing Taylor series expansion of fields in their variations and stuff. And this is very much encoded in here. So of course you can speak about variational calculus without this tool, but the statement here is that this is kind of secretly in the background. This is the archetypical geometry that models infinitesimal variations. And so this is like bare bones fields. This is like, okay, if you have a Lagrangian, if you want to look at its Euler-Lagrange equations, then you're secretly using these kinds of generalized charts. But now that we're using some coordinate functions that square to 0, we can kind of keep going. And that's where the supergeometry comes in, so this R0Q is like a DQ. It's like an infinitesimal disk of dimension Q, and it's also first order infinitesimal because the coordinate functions here on this thing don't just have the property that their square vanishes, but they also have the property that any two of them actually anti-commute with each other, right? As you know. So this is very much like an infinitesimal disk, the superpoint, but with the additional property that things anti-commute, which implies that as infinitesimals, this has actually to be first order. That's why we don't write an index subscript 1 here. So that captures a common theme. Like people have slogans like, "Oh, fermions behave like they are very small" or something. This has to do with the fact that these are really infinitesimals. And this, so using these charts here, so I'm writing products here, so we can easily envision, one can easily define, it's clear what it means to take the Cartesian product here, to have a space that has n ordinary dimensions, m infinitesimal dimensions of order k, and in addition q super dimensions. And all this is one, what I would call formal super Cartesian space. And the category of these serves as a site for actually formal supergeometry, where formal doesn't mean undefined or something. It means it has these formal power series algebras here. And I just want to amplify, this is maybe a tautology that might be underappreciated commonly, is that even though it's called supergeometry, this is a term invented really by mathematicians, this has nothing to do yet with supersymmetry. The supergeometry just refers to the fact that we have these odd coordinates. There's no assumption here that anything is supersymmetric. In fact, you need exactly this geometry. This is an important point whenever you consider classical field theory with fermions, as of course you do in the standard model, say, or in any other field theory with fermions. The fermions on in any classical field theory do not actually form an ordinary geometry. By the Pauli exclusion principle, the corresponding fermionic fields classically are anti-commuting fields. And that is important for instance, the Lagrangian density for the Dirac operator, something like psi bar d psi. If psi, let's forget the bar for the moment, psi d psi.
Sure.
If psi were an ordinary bosonic function, then psi d psi would be a total derivative. It would be d of 1/2 psi square, right? That's psi d psi by the product rule. So the standard, already the Lagrangian density for a standard Dirac field, for any fermionic field, the free Lagrangian density for a fermionic field, would not actually make sense without having anti-commuting. It would just disappear. It would become a total derivative and drop out. It wouldn't exist. So this is really necessary in order to speak about classical field theory with fermions, which is kind of a big deal, actually, right? If you want to be precise. Right, and then it continues. Shall we keep going through the list? So these three are...
Yeah, but you could breeze through it. You can go through it quickly because I noticed we're only 35% done.
Yes, this was... Should I speed up? Yeah. So these three...
Yeah, speed up.
These three are kind of bread and butter. Everybody needs them. And then we come to more still important, but more, how should one say, exotic aspects of physics. So we might ask, well, what if we now have a gauge theory? Then our spaces of plots themselves should not just be sets. So here we talked about them being just sets. But of course, for a gauge theory, for example, if X is something like the configuration space of gauge fields, then a plot into it, any two plots into it may be distinct and still related by gauge transformations. So they should actually form a groupoid themselves. And the way to do this, okay, being quick now, is one kind of throws in the rudimentary information of what it means, of what it means that there are transformations. And a transformation, like a gauge transformation of order R, first order, second order, and so forth, it goes by this symbol delta R. So this is a bit technical. This is notation for the simplex. That's one way of encoding transformations and higher gauge transformations. So throwing in kind of directions in which things can gauge transform gives us a notion of charts that models gauge theory and higher gauge theory with fermions and blah, blah, blah. And then I can go further, specifically in string theory, but also in in other areas, it's important that spaces, like spacetimes, are not actually smooth everywhere. They may have what's called orbifold singularities. So we can ask our probes to have actual singularities already in them, so that we can detect singularities in the target space. So this is notation we invented. This is supposed to be suggestive of a little singularity. You see, like a little
yes,
cone here, which has a G, which kind of comes from a G action. It's a quotient by a local G action. And finally, and this gets us really into deep waters here, one can throw in something that behaves like negatively, like spheres of negative dimension. And yeah, let's talk about this another time. If one does this right, then this actually boosts the corresponding spaces that are probed by this to being parametrized, what's called parametrized stable homotopy types. And this is kind of fascinating, actually. This is really where the quantum aspect comes in, where the spaces we're talking about kind of acquire a linear halo of quantum operations around the classical geometry.
Briefly talk about what it means to have a negative dimension on a sphere.
Yeah, exactly. I could show that. So we effectively define a category of charts of these d minus n's that where the maps behave like maps of spheres, but the direction which the arrow goes is as if they were of negative dimension. So it's just a notation for a certain category of things, where the main point is that after we apply the Yoneda lemma and think of these charts as being spectra, as it were, like spectra of spaces, we will see the sphere spectrum in different dimensions.
Okay.
Yeah, let's move on. So this is from the end section of this encyclopedia article.
Okay, great. So we'll leave a link to this in the description for people to learn more about.
Yeah, I'll put it. So here's the category. This is what the category. This is actually now a higher category of these negative dimensional sphere looks like. This shows which maps it has, which transformations, and it explains how this thing. So this needs a bit of thought. This should not be done too quickly. I'm just claiming this maybe for the moment, but you can find the pointers here. But this is of course important eventually to bring in the quantum aspect. All right, yeah. So that's our examples, and now let's see. So what I'm going to do now, and now I finally come to these animations that I have. So now we want to find it. So this is the end, I think, of my of the little introduction to category theory in physics that I have here. And now we want to see it at work. We want to see things happening. We want to see this promised emergence of stuff out of this substrate that we built. And I'll be talking now about mainly this topos, this sheaf topos that we get by using the first three at least, and possibly the others as our probe spaces. And that, in the writings I have, this goes by the name of superformals. So the generalized spaces that are probed by all this here, sometimes called superformal smooth infinity groupoids, for the fact that they're smooth, they're probed by the RNs, formal because they are probed by infinitesimals, super because they can be probed by super-Cartesian spaces, and higher groupoids because they have these high gauge transformations in them.
Mm-hmm.
All right? So that's the topos we have, and now let's look at one of the. So I have these animates. This is a bit experimental, of course, as you know, but let's see what happens. So this is like a slide that keeps building itself.
Okay. Note to the viewer: the animations in this talk loop. This means there's no need to pause, because if you wait just a few seconds, you'll see the same thing again.
And what I want to do now is I want to talk about how in such a topos we now have a system, a progression of dualities of modalities. So remember, dualities means adjunction, and modalities is something I'm explaining here. So I want to apply the following method, as it's called, now to this topos of physics, and see how things emerge in this. So we're going to be looking at a category H1 here, which. So I'm just calling it H1 because at this point it could be anything. But you should think of it as being our category of generalized supergeometric spaces of use in physics. And we're going to see that it comes equipped with various functors to a base category, which is here called H0, which you may just as well think of for the application that comes as being the category of sets, just bare sets. And this functor, for instance, here, from our very generalized spaces, two sets will be the functor that extracts the underlying set of points.
Okay.
So if we have a generalized space, we can just probe it by our zeros and just ask, well, what points do I see in here? And that yields a set of points. And so if H0 is the category of sets, we get a functor here. What is being shown here now is that if we have systems of such functors that are adjoint in several ways, then we get corresponding further structure. Let's first look at these two. Suppose our base functor here, say the functor that assigns points from H1 to H0, suppose it has a right adjoint. So this symbol here, in just a moment, we'll get back there, a functor, and here is a right adjoint. So this symbol means that this functor is left and this functor is right adjoint. Now, when we have that, we can go back and forth. This is what this arrow is indicating. So if we have these functions, we can go back and forth and get a functor that is called sharp here, that goes from H1 to itself.
So you're showing that all of this that's emerging or that's being displayed with this auto-playing PowerPoint or what have you is canonical. There's nothing extra that you're adding. It's already there?
Yes. So, well, okay, I do this in stages. So on this slide, I'm saying if I have sequences of adjunctions, then, and the rest follows. So, yeah, very good. Thanks for asking, actually. I should have made this clearer. So what is given here is adjoint functors and other adjoint functors, and I'm unwinding what extra structure that implies on our category.
Yes.
But in a moment, we'll go, so this is just the explanation of the method. In a moment, on the next such slide, we'll actually apply this to our topos of supergeometric physical spaces, and we'll see what functors actually exist there, and only certain ones do. And so then we see a certain dynamics emerging, right? Okay, so here's just the explanation. If we have an adjunction, then we get this end of functor. If we have another adjoint on the other side, well, we get another end of functor here. And these two functors are adjoint to each other, as one can easily see by digging through the algebra, by following through the definitions. If you have an adjoint triple, as people say, then the corresponding end of functors are themselves adjoint to each other.
Yep.
Now, them being composites of adjunctions, it means that these co-unit and unit maps exist on them. So if we have this adjoint pair of monads, or modalities, as I'm actually going to call them, on our category, then it means that every object in our category H1, so every generalized space, now has kind of this flat, as we're going to pronounce it, and sharp. It has this flat aspect to it. So for every aspect, every object, right, we can apply flat and get kind of this version, or we can apply sharp and get this version. And the co-unit and the unit are maps like so, that arrange this little diagram, so every x is sitting kind of in between these two extremes, as it were now, because remember, every adjunction is like a duality. So in some sense, this flat x is dual, opposite, we should say, to this sharp x, and x is in between. And in fact, this kind of means, so once we have an understanding of what this flat, like, you know, I haven't really defined things yet. It's just, suppose we had, but once we know what flat actually does, we know what this extreme aspect is.
Yes.
And once we actually have sharp, we know what this extreme aspect is. And then just by the fact that these two functors exist, already makes every object kind of be in between these two extremes.
Yes, okay.
And for the case that will appear in just a moment, where flat and sharp are the discrete aspect of a space, like the set of underlying points with its discrete topology, or the set of underlying points with what is called its co-discrete topology. So, like what's sometimes called discrete and co-discrete space, it will mean that every space in our category is in between being discrete and co-discrete. But this is exactly what a topology on a space means. Every topology is in between, in some sense, the discrete and the co-discrete topology. So it's a rudimentary, what we see is
interesting,
getting towards a rudimentary form of encoding some spatial property in our objects, just by the fact that there are these opposing aspects of things.
So I see here pure nothing and pure being.
Yeah, it starts to appear now. So this is what we'll see more in the next diagram. But I'm just amplifying here that our base topos of sets here has a canonical functor down to the point, where the point now means the category, which is the singleton category with a single object and only an identity morphism on it. And one can check, one can see that this functor has a right adjoint if and only if if we assume that H0 is the category of sets, then this right adjoint exists. The right adjoint to the functor to the point exists. So it will choose a single object in H0, since the point has a single object. So our right adjoint functor will have to choose a single object. And then one can check that the laws of adjunction say that single object has to be the terminal object, the object such that every other one has a unique map to it.
Right.
And similarly, one will see that now I'm almost catching up here with the left adjoint exists. It will have to pick the initial object. So that's why these functors are the functors constant on the initial and on the terminal object. So that means that every object is in between pure nothing, like the initial object, or pure being, like the thing that is, but in its most trivial form. And this is, of course, tautological in itself, but it is an opposition, and it is one of these dualities, and we'll see that it serves as the basis for a whole tower of such dualities that we can see. For instance, we can next ask for yet a further left adjoint here. It will produce yet a further end functor, and they will arrange in such a tower in such a progression, as I say, of modalities, of ways that things in our topos can be. So that is the method that I'm going to show in a moment, and this comes maybe finally to our first little punchline here. I'm going to now look at this progression in the next animated slide. We'll see this progression in following these rules at work in our topos of supergeometric spaces, and we'll see what is it that emerges out of this initial opposition between nothing and pure being. And it turns out there emerges a very interesting.
So I noticed it says that this is part of some work that was just a decade old at this point, and it's inspired by Levin, who was inspired by Hegel.
Yeah, this is right. Yeah. So okay, right. I should have said this. So this is really in sketch form at this point here. I mean, the slide isn't maybe showing everything that one could say here, but this is really what Levin came up with is what's actually going on in Hegel's Science of Logic. So Hegel, in the Science of Logic, in this old book, he kind of puts himself into the place of a seer, of a mystic. He just looks inside himself and says, "Okay, let me forget everything about, and let me just kind of concentrate." So he wants to make philosophy a science. He kind of feels his way to the beginning of every thought, and so he argues himself in a kind of poetic way into this kind of story where he says, "Okay, so if I really abandon all other thoughts, what do I have? Well, I have nothing." And then he, over pages and pages, he talks about this pure nothing that he's pondering. But then he gets to the point that he says, "Well, I've been pondering pure nothing now for quite a while, so apparently it is something, right? After all, it exists." So, and then he feels that there's a certain internal opposition happening where the pure nothingness that he assumed to have started with kind of gets into tension with something that just exists, with the pure being. But then he says, "Well, but this can't quite be because we had nothing there," and so he kind of feels an inner tension, which eventually he says is being resolved out of this dynamics, really, this logical tension, is kind of, he feels it like a dynamics that makes something else emerge. And Levin's observation was that this is really accurately captured by what I'm drawing. This is not quite how Levin drew it. That's what I'm drawing as this progression of these modalities. So Levin observed that from adjoint triples of functors, you get these adjoint monads or adjoint modalities that express opposing dual opposite aspects of one thing. And then I can ask there for a further such opposition, which resolves the previous one in that, so as the composition of the functors up here implies, the things that are purely sharp for the sharp modality actually include both nothing and pure being. So in this sense, the opposition between these two aspects gets resolved or unified in this opposition because
I see.
Both nothing and pure being becomes what I guess Levin likes to call becoming, because that's kind of what matches here with this terminology, which then has this other duality to it, and so forth. And then you have another opposition here, and one can, and I'll try to do that at some point, which I guess you can find on the nLab page on Science of Logic. You can now ask, well, what is this next opposition if you were to actually compare it to Hegel's poetry? And then one can actually see that it does sort of make sense that Hegel sees another opposition, which again, that's kind of what he calls the process, the progression, where there's intrinsic oppositions that get resolved only to find new oppositions to get resolved and so forth. So this is I guess, what's sometimes called the dialectic method or something. And Lavier's insight was that this Hegelian poetry, as I would call it, actually is nicely matched to exactly this math of adjoint monads, of, I guess he calls it adjoint cylinders. Right. And so what we do now is we say, okay, now we've actually formalized the science of logic. So now we can run Hegel's experiment, which he had to do kind of without tools. We can now ask, so, okay, what is it that emerges out of the primordial nothingness? And so what is it that emerges if we just keep playing this, if we keep growing this tower of modalities here? And so that is what I'm showing in this next animation. So I should say I've typed this a few years back here, so I didn't retype it. So it speaks about infinity groupoids all the time. You may just think of these as being sets, the way I've introduced things. So not to get hung up on this. So the basic, what we're seeing here is this. This full topos of generalized supergeometric spaces on the far left, it just disappeared. And we're looking at this kind of situation that we just explained in the abstract. A functor all the way down to the point, which then successively factors through subtoposes. First of sets, the bare, geometrically discrete things that have no geometry on them, just points. And then we'll see that there's further factorizations to a category of the reduced spaces, where reduced is in the sense of reduced schemes as it's used in algebraic geometry, meaning those that have no infinitesimal extension, that are just ordinary non-infinitesimally thickened spaces. The technical term for that is reduced. And then as a further subcategory, we'll find in a moment here appear the bosonic parts. Just a moment, here it comes. So this is the subcategory of all those spaces that, even though they're potentially supergeometric, they just happen to actually have no fermionic aspects to them. They're just ordinary bosonic spaces. And so the point here is that these adjunctions that on the previous slide I just assumed, I said, well, suppose we have them, then what follows? They just appear now here. There's no way, these adjunctions, they exist. If they exist, they are unique. So you either have them or you don't have them. So we just feel which we have, and this development down here shows how successively these adjunctions factorize in such a way. And then for each such pair, so all these little symbols are missing here. So every arrow on top of another one is left adjoint to the one at the bottom. So whenever we have such a pair going back and forth between any of these topos, this means there's a corresponding modality induced, a certain operation on H, I should say here, that is given by going all the way down here and coming back. So that will extract some extreme aspect, physical aspect of our spaces. And the corresponding progression of these extreme aspects is shown here. So we start with a opposition between pure nothingness and pure being, as we did. So that's at the very beginning of this animation. That's the functor that goes all the way down to the point and just comes back. So nothing really happens, but still there's an initial opposition between every object sits between the initial and the terminal object. And then we observe that this gets resolved by this next operation, which is just the one we've shown before, sharp, which in fact plays this role of forming the co-discrete objects on the underlying points of a given space. So we see that things become spatial in some rudimentary form. There's a discrete aspect and a co-discrete aspect there.
Yes.
But then further adjoints appear. The next one that just disappeared here is the so-called shape modality, which says, well, that apart from just having discrete and co-discrete aspects based on the underlying points, there's actually also a shape to our spaces that is not just embodied by the points. So the shape operation in the actual model corresponds to forming what's sometimes called the topological realization of an infinity stack. So it's the thing that kind of, sees the actual homotopical shape of something. That's why it's called a shape. So more and more of such aspects appear. Then after the shape operation, there's infinitesimal version of the flat and the shape. There's something that sees an infinitesimal shape of things, which in algebraic geometry is known as the Dirac stack monad. So these are things, I gave them some symbols here, but these are things that are known in algebraic geometry of derived schemes, of formal schemes. The reduced aspect, the co-reduced or the Dirac stack aspect. And it keeps climbing, and that's interesting. So we're just asking in this Hegelian Leverian notion. So Levier never pushed this, it seems to me, beyond this first step. I think he looked at this first step and had some examples, some toposes realizing that which were a bit contrived. So I don't think he looked at examples that are kind of practically important. And the insight here is that actually applying this to our generalized categories of physical spaces, not only does this have some importance in itself, but this progress actually continues and kind of discovers or rediscovers, one could say, these various aspects that our spaces have, like the pure being aspect, the differential topological aspect, the homotopical aspect, the infinitesimal aspect. And then next, and that's interesting, it rediscovers the fermionic aspect. So there's now a modality of being bosonic or being bifermionic, and then it finally ends. And what is interesting now, and I haven't previously talked about this, maybe I should have made a dedicated slide for that too, is that the modalities that appear in the middle here, and now it would be good, of course, to be able to stop this animation. I can't, so we have to just live with it.
Okay.
But the three that appear here in the middle, they are special in that these three are given what is called by localizations. So you can ask, well, how do we compute the shape or the infinitesimal shape or this rheonomic aspect of a space? Well, it turns out the shape or the topological realization of an infinity stack is the answer to asking, well, what if I had this space and I want to just look at its homotopical meaning that the real line being as it is contractible, having no homotopical content, it just has smooth content kind of, but if you forget that, you can shrink it to the point. So what if all the line plots and all the Rn plots into my space, if they're actually not equal but gauge equivalent to the point, what is it that remains if what can I still see in my space? And that is like the technical construction that I'm alluding to here is saying that the shape monad is actually what's called the localization at the Rn's. So it shrinks them away and asks, what is that remains? And that's why it's called the shape. It's you no longer see local differential structure, but you still see some global shape. For instance, the circle, if you look at the shape of the circle, then you end up with what's sometimes called the categorical circle or the simplicial circle. It's you not only have a smooth manifold, but you still have kind of the rudimentary information that there is a point and there is a way of going once around and come back to that point. So just this global gauge transformation, that there is a large global gauge transformation, is retained. Right. And so I said this, so the three modalities in the middle, they have this property that they're all localizations, and as such they pick out a distinguished object. So the shape here picks out the continuum line, the Rn, the R1 actually. So it knows there is the continuum, whereas the infinitesimal shape modality picks out the one-dimensional disks, the infinitesimal intervals.
Yes.
And then finally, and that's kind of the punchline here, now it just says disappeared again, and then finally there is one more, it's this rheonomic, as it's called.
So it introduces fermions?
Yeah, that is the one. So this level here, this line that is going to appear in just a moment, that is the one that knows about the fermions, bosonic aspect, rheonomic aspect, bifermionic aspect. And this guy here is given by localization at the superpoint. So it's in this sense that this progression discovers first the continuum, then the infinitesimals, and then the superpoint as being the objects that characterize this whole progression. And so it's in this sense that, as this diagram keeps showing, that we kind of went, just by applying this, what Hegel called the objective logic, we kind of went from nothing to finding, geometric structure culminating in the superpoint here.
So in this diagrammatic playing of nothing to a superpoint, a so-called superpoint, is there more than just analogies here? Is there a rigorous proof behind this?
No, there's no analogies here. It's just, all this is a proof. Like what I'm showing here is just a fact. So I'm kind of illustrating a theorem here. It's a fact that this progression of modalities and adjunctions exists in this topos, right? So that's just a fact. And so I'm saying if this topos is our Platonic world in which we live, then we can play the Hegelian game there and ask, okay, what is the structure that we see emerge out of the initial opposition of nothingness and pure being? And then it's just a fact now. This is a theorem. It's not an analogy or something.
Is this theorem going back to 1965 from Grothendieck or to 2013 with you?
No, that's my observation.
So this is quite recent.
Yeah, so this is what I wrote in this habilitation thesis, differential cohomology in a cohesive topos. Yeah, right. So the thing is that, as I just mentioned, so even though Levier, he made this, I think, what one should call a big accomplishment of suggesting this formalization, he didn't really dwell on convincing examples. He had some, I think, that could fairly be called contrived examples that just showed the math at work, but didn't really show, much practical use. And what I'm observing here is that in the actual topos that we actually want to be using in physics, that we are using, implicitly or not, that not only does this initial stage exist, but it keeps progressing, and it knows about these archetypes of our geometries, the continuum, the infinitesimals, and the superpoint.
Beautiful. Okay, so what else is there? If you've shown almost everything from nothing, it's not just something. It's quite a plethora from nothing.
Exactly. So now
what else is there?
So now let's go further. So this is some backdrop on the higher topos theory that is maybe needed to formalize or just to phrase basic physics, field theory and stuff. So let's see what more fun we can have now that we kind of got the superpoint experience. Here's another incarnation of this, another rendering simply of this progression that we've just seen. But let's maybe keep going. So now let's see. So I'm now making this fun-sounding claim that actually from the superpoint emerges 11-dimensional supergravity. And if we have the energy, let me maybe try to explain that. So now let's play with the superpoint in our high topos. And the thing is,
there's a pun there. If we have the energy.
Oh, I see. Yeah. Yeah. Let's see if we can go through this. So now I'm going to look. So we have this kind of atom, as one might call it, the atom of space or of superspace, kind of came to us in this emergent form. It's not sitting anywhere yet, right? It's not a space. It's a zero-dimensional space, but it's not anywhere. It's just kind of the concept of this space that came to us. But now let's kind of hold a microscope over this superpoint that just emerged and see what extra structure is in there. And of course, there's other universal constructions we can do with adjunctions. We can look at what's called universal central. So the superpoint carries the structure of a super Lie algebra. It is, as such, the abelian super Lie algebra on a single odd generator. And with that structure, we want to ask, well, what kind of emerges out of that object, in the sense of now in a more, how should one say, more classical sense, that we ask, what are the universal extensions in the realm not just of super Lie algebras, but of higher super Lie algebras that emerge out of it? And it's a fun exercise, which originally started with John Huerta in this article here called M Theory from the Superpoint, where we showed the root of the following. We proved the root of the following extension. So it turns out, if you start with the superpoint here and play the following game, that in each step it doubles the fermionic dimension. So it takes the odd one-dimensional superpoint to the odd two-dimensional one, and then forms what's called the universal central extension equivalent under, so there's a technical thing here, equivalent under the external automorphism group. So there's some intrinsic equivariance condition one can compose. And then again, it's double, form the extension, double, form the extension, double, form the extension. Then this process discovers it runs exactly through first the superspace times in which Green-Schwarz superstrings exist. So kind of the I shouldn't say critical, the dimensions in which superstrings can exist. And then it keeps going. So let's talk about the first step here. So this extension here, so what is going on here? So let's talk about this. R02, in which sense? So this is still just a superpoint. So the first interesting step is happening here, where I suddenly claim that three-dimensional n=1 super-Minkowski spacetime with its supertranslation, Lie algebra structure, emerges from R02. So how can this be? Well, let's think about it. So we're looking at extensions. So an extension of a Lie algebra is classified by a two-core cycle, right? By a degree 2 element in the Chevalier-Allenberg algebra of the Lie algebra. So a map from the graded commutative second power of the Lie algebra with itself, a map from there to the ground field, which satisfies some cocycle condition. And now, since our superpoint has a single odd direction, such a two-form on it, which would classify an extension, is actually a symmetric form, since it's an odd two form on an odd space. So what we're really asking for this first step here, that just reappears again, this first step here, we're asking kind of for the maximal invariant number of symmetric forms on just R2, on these two odd coordinates. But since we're working over the real numbers, these are just the symmetric real matrices.
Sure.
The Hermitian matrices. And there's a standard fact that the space times in these dimensions here, dimension 3, 6, and 10, can equivalently be understood as being the Hermitian matrices with coefficients in the real numbers, the complex numbers, and the quaternions. And this kind of explains. So I was trying to kind of indicate how the proof works here. This explains how this first step can happen here. The two independent, non-trivial two cocycles on R02 are exactly the information that encodes the information of the three-dimensional super-Minkowski spacetime. And then it continues this way. And it's quite interesting because the process down here in this root of the bouquet of the tree is all in super Lie algebras. So these are all super Lie algebras, and we're recovering the super translation super Lie algebras of these Minkowski spacetimes. But then at some point, there is no further invariant extension, but there are now higher extensions that produce. So here's 11D super spacetime. So there's further extensions now here that are not extensions of super Lie algebras, but are what are called super L-infinity algebras. So higher categorical Lie algebra extensions. And they turn out to correspond first to the strings, so the F1 branes in these dimensions, then to the corresponding D branes, then from 11D to the M2 brane and the M5 brane.
In which sense?
In which sense? Let me say in which sense this is true. Let's focus maybe on this top guy here. So here's a statement that on 11-dimensional superspacetime, like the Minkowski form, the flat or maybe infinitesimal locus of any space. So there's There's an extension now by what's called the M2 algebra, the M2 Lie 3 algebra. So there's a 4-core cycle actually on super Minkowski spacetime, like the ordinary extensions of a super Lie algebra by another super Lie algebra are encoded by a 2-core cycle. This is standard textbook material. Now you could ask, well, what is it that a 3-core cycle classifies? Well, it turns out a 3-core cycle on a super Lie algebra classifies an extension by a higher form of super Lie algebra called a Lie 2 algebra. And so this happens with some of the D-branes here. But this one, the M2 brane, is classified by a 4-core cycle. And that 4-core cycle is the famous the famous bifermionic expression on superspacetime that is known to be the bifermionic component of the supergravity C field on 11-dimensional superspacetime, but it's also what is called the Western term of the Green-Schwarz sigma model, of the kappa symmetric sigma model for the M2 brane. So here we see the expression. Mu M2 is this 4 cocycle. Oops, that was too quick. We'll see it again. So what this diagram, what we call the brane bouquet, as a variation of the old name of the brane scan, which just tabulated the sum of these branes by computing certain super Lie algebra cohomology. So this brane bouquet kind of discovers from the superpoint now first the super spacetimes of kind of the right dimensions, then the superstrings in their Green-Schwarz incarnation as sigma models, the D branes, and then in its kind of tip here, the M branes. And the key point now that is interesting is that, so this is a 4 cocycle that classifies the M2 brane extension, which again in turn carries a 7 cocycle that classifies one further extension corresponding to the M5 brane. So again, the 5 cocycle happens to be, the 7 cocycle happens to be either the bifermionic piece of the dual C-field flux 11-dimensional supergravity, or equivalently the Western term for the Green-Schwarz sigma model, Green-Schwarz type sigma model of the M5 brane. And it's these 2 cocycles that we want to be focusing on, which are shown here. G4, oops, it's gone again. But we'll see it. So the punchline is, and let's look at it one more time and then we'll over. So from the superpoint, we discover that up in 11-dimensional superspacetime, there is this pair of cocycles, a 4 cocycle and a 7 cocycle, which are in a crucial relation to each other, which mimics just the equations of motion of the C field in 11-dimensional supergravity. And it just comes out. It's just kind of built, in some sense, built into the superpoint here. And it kind of grows into this, it blossoms, if you will, into the structure up here.
Uh-huh.
And then in the next step, I want to show how we actually obtain like full supergravity from this. Because this is just local model space. All these are super Lie algebras. You should think of all these things appearing here as being what in an actual space-time you would see in the infinitesimal neighborhood of any point. Like on a tangent space. On a tangent space, it looks like a super Minkowski space-time, and there we have these cocycles. But now let's look at the following theorem. So we proved this just last year, actually. So it turns out, if you ask, I'll show it. Maybe I'll show a better version of this in a moment. But if you take these 2 cocycles that ended up being the tip of this diagram here that classified the M2 and M5 brane extension, and we ask that they globalize now over a non-flat curved superspacetime, so that roughly if you have some superspacetime, which exists in our topos by the previous construction, so that every tangent space carries in a consistent fashion this cocycle.
How so?
So if it globalizes, if you can kind of move it in the sense of Cartesian geometry, of moving frames, if you can move these cocycles over your curved manifold, then that requirement alone is actually equivalent to the full equations of motion of 11-dimensional supergravity. So it means that your super spacetime is actually a solution to the Einstein equation in 11D, that it carries the super Einstein equations where the gravitino field satisfies its Rorita-Schwinger equation, and on top of this, the supergravity C field, so the gauge field of the theory, satisfies its equation of motion. And that is repeated again on this animated slide. We're just sketching it here. So what are we seeing here? I'm now going. I guess I've changed pace a bit. So we're now looking at how to see full supergravity actually appear from these ingredients that we discovered. And okay, what are we seeing here? So we're looking at a super spacetime, an 11-dimensional super spacetime. I didn't show I'm not showing the odd coordinate components. Maybe I should have added them.
Sure.
So this says odd dimension 32 as befits n equals 1. So this is a spacetime that is locally modeled on the tip of this emergent diagram that we saw. It's locally modeled on this 11D super spacetime. And we're asking, that on this space-time, we have two forms, superforms as it were, of this form, where G4 is of this form. And this is just, even though it was too quick maybe to see it on the previous slide, but it's just exactly the 4 co-cycle that classifies the M2 brane extension. So this is kind of the intrinsic supercomponent that knows about the existence of the M2 brane. And similarly, for G7, we have this bifermionic expression. And so we're asking, well, let there be forms that, saying we have a super space-time, but this, it is equipped with a supermetric structure being a space-time, and the metric structure is, since we have fermions in first-order form, so it's encoded by these field-bind forms. So everything is expressed in these field-binds, which are the things that locally identify the space-time with Minkowski space-time. So we say, okay, let there be two flux densities, as we're going to call them, whose bifermionic component is exactly the one that is kind of God-given, and then let them have, in order to patch it up, let them have any other ordinary component, an ordinary 4-form, ordinary 7-form component. And then this co-cycle condition that makes these things be co-cycles that appeared in the previous diagram are exactly these equations here, that G4 is closed, and G7, that the differential of G7 is the square of G4 up to some factor. That is the co-cycle condition that, I'm just saying this now, I haven't fully explained this, but it's clear that G4 being closed, it's an element of the Chevalier-Eilenberg algebra or L-infinity algebra, and it's being closed, that's just a co-cycle condition. And then one has to just see what it means for the M5 brane extension to be a co-cycle, which is not defined down here, it's defined up here. So kind of pushing it down makes a co-cycle condition be this equation that says that d of G7 is G4 square. Okay, I guess, I don't know, it's maybe getting a bit technical here, but the thing is that this bottom piece here, so this information we're requesting on each tangent space, is the piece that came to us from this progression. It emerged to us kind of from nothing. And we're now asking just for that structure to be globalized over a space-time. And so the first thing we want to do is we want to ask, well, in order to put this into a proper categorical formulation, we need something like a classifying space for the solutions to these equations here. So the key co-cycle equation of our fluxes were that one of them was closed and the other one had the differential equal or proportional to the square of the other. So we ask, well, what is that? What is it that classifies pairs of differential forms with that property? That's what I'm asking here. And it turns out that this is exactly what is the structure of differential forms with coefficients not in an ordinary Lie algebra, but in a higher Lie algebra that is called the Whitehead L-infinity algebra of the 4-sphere. So there is a way of assigning to each, under multi-technical conditions, finite type, rational, finite type, to each topological space, an L-infinity algebra whose ordinary bracket is what's called the Whitehead bracket of that space. So it's some kind of infinitesimal approximation, in a way, or rational approximation actually, to the homotopical structure in a space. And the space that appears here, the space that happens to encode just the co-cycle relation that finds these M2, M5 brane co-cycles, happens to be the 4-sphere, or any other space of the rational type of the 4-sphere. So that we can recognize the information we need here, the local form data on our manifold, as being exactly flat or closed, one should say, S4 valued differential form, which has these two components. And the flatness encodes exactly this co-cycle condition, which is actually equivalent to the supergravity equations of motion. So you see what we have achieved here now is that we have encoded the equations of motion of supergravity in a kind of purely cohomological or rational homotopical construction. We would just say the fact that a space-time satisfies supergravity equations of motion just means that flux densities of this form exactly arranged into a four-sphere-valued flat differential form, where by four-sphere-valued I mean valued in the Whitehead L-infinity algebra of the four-sphere. And that is of enormous use now, because as you keep seeing in the diagram that builds here, we can now ask, what is the global field content of supergravity? So this is now getting us into an actual new physical realm. So I make the bold claim that this has been, to a large part, not completely, but to a large part, actually be ignored. It's known for a long time, like for now almost exactly 100 years, that in electromagnetism, that of course the electric and magnetic field strengths that Faraday and Maxwell talked about in the 1850s are not the full field content of the field of electromagnetism. There's a global aspect of the field of electromagnetism, which sometimes goes by the name of Dirac charge quantization, or of existence of magnetic monopoles or something. So there's some global structure which is not entirely seen by just the differential form data, that is the flux densities of the fields. And what we're seeing here now is that the same question that Dirac sort of answered, at least in hindsight, in the 1930s about electromagnetism, can and should be asked about all higher gauge theories, in particular about our supergravity theory, with these where this 4 form and the 7 form play the role of higher analogs of the Faraday tensor 2 form of electromagnetism. And so we want to ask now, what could be a global completion of the field content of a Levin-dimensional supergravity that, in addition to this local flux data, knows about global topological structure encoded in the field, knows about global charges that could source these fluxes. And the diagram that keeps building up here and disappearing again,
yes,
that shows how these things can be done. So now that we know that the field content of the fluxes is encoded in something with values in that part of the force sphere that is detectable by differential forms, well, we can ask for a classifying space to be called A here that classifies the actual global charges, not just approximated by differential form data. And then we just want to ask so this would, like in electromagnetism, this would be the monopole sector, classifying space for the monopole sector. And so we ask, where are these things comparable, so that we can ask, these charges source these fluxes, and as such they're compatible, right? Not every set of charges is can source given fluxes. So there needs to be some compatibility condition to them, right? If you have a magnetic monopole somewhere, it sources very particular fluxes and not any fluxes. And so that question of where these things can talk to each other so that they can be compared is answered by the top part of this diagram, which appears now in just a moment. So it turns out that we can push forward, we can send these closed differential forms to their what's called their moduli stack. Anyway, some deformation space for this.
Sure.
And that receives a map in this higher topos from any space which has the property that its Whitehead L-infinity algebra coincides with that of the force sphere, which means that its R rationalization is that of the force sphere. Any such space can be put here, and any such space has such a map. It's the character map, the generalization of the Chern character in K-theory. And so this kind of answers the question of what is it that serves as consistent flux quantization laws for Levin-dimensional supergravity. It's any space, classifying space for the charges as any space, subject to the condition that it's kind of the part of it that can be seen by differential form data is the same as that of the force sphere. And then if you choose any such space, then the full field content of a field in Levin-dimensional supergravity is then a homotopy between the charges to the fluxes in this diagram, in this diagram as it lives in our higher topos. Of course, the canonical choice for A is the force sphere itself, not the canonical choice, like the initial choice, the simplest choice. And so what we've been calling hypothesis H is right? So this diagram, the upshot of this diagram is twofold. It says, well, first of all, here's the actual rule how to globally complete the field content of, well, any higher gauge theory of Maxwell type, first of all, but specifically here now 11-dimensional supergravity, which is an example. And second, the second thing is, well, there is actually among the infinite set of possible choices for the charge quantization, there's one choice that is kind of singled out as being it's the simplest one. It's, for instance, in terms of CW complexes, it's the one with a single cell, the simplest. It's just as the four cell. And but anyway, whatever choice you make, it gives a definition of global field content of 11-dimensional supergravity, which has not found much attention before. There is articles by Diaconescu, Fried, and Moore from a few years back who talked about a model of the C field, which went in this direction, but wasn't quite comprehensive, I would say. And here we say, first of all, well, look, here's a choice to be made, and second, there is a specific choice that kind of stands out. And you see, what we're seeing here is that the usual data that goes into field theories, as they usually formulate in Lagrangian form, this differential form data is not in general, and we know this from electromagnetism, is not in general the full field content, actually. It's just kind of chart-wise field content. It's lacking all the global structure. So first of all, this is saying, what is it that actually completes, in this case, 11D supergravity globally?
Yes. So hypothesis H is a claim about the classifying space?
Yeah, right, but the classifying space is part of what characterizes the full field content. So hypothesis H is a hypothesis about what is the global completion of the field content of the 11-dimensional supergravity, in analogy to how.
Yes.
So you see,
I see.
So I don't have a special slide for this, but let me just say it in words. So let's go back to electromagnetism. So what happened in 1850? Maxwell writes it in modern language, right? He writes a two form, F2, so such a G with two indices, and says that is the electromagnetic field. So it's built from its components are the electric and the magnetic field. But it's a two form. It's closed and satisfies some other conditions.
It's a field strength, technically, as we would call it.
Yeah, exactly. The field strength, or if you integrate it over a sphere, for instance, around a monopole, it measures the flux through that sphere that emanates from the charge that is carried by the monopole.
Yes.
So that's why we also call it the flux density. That's maybe a more suggestive term here.
Sure.
But the flux density absolutely is just another incarnation of the field strength. Yes. Sorry. And so then the decades pass, and 1931, with a bit of paraphrasing, Dirac comes and says, no, this cannot be the full field content of the electromagnetic field. And he really says two things at this point. He says, well, first of all, there must be a gauge potential. We must locally be looking for one forms A, right? The so-called vector, the gauge potentials, such that our F,
or the connections.
Yeah, the connections. The local one forms, so that F is the differential of these A's. But that alone is not actually the full insight, because it's quite interesting, because that is something that already Faraday was actually playing with. Faraday and Maxwell both, they had a funny term for this. I could look this up somewhere, I forget now. They couldn't quite nail it down, but they recognizably realized that something like what we now call A is actually a good way to encode the field equations. But this is not the full insight. Like when you see discussions, for instance, of all these supergravities, you say people often write down potentials for these things here. They write a C3, a 3 form, and such that G4 is DC3, right? So
yes,
that is the analog. But that cannot be true globally. Like we're interested, if there's non-trivial charge in our spacetime, then this G4 is not exact globally.
Yes.
It measures a certain Ram class, which is kind of a rational image of this full whatever A cohomology class we're seeing here. And so the whole point really of the global charge is that G4 is not generally globally exact. So there's not actually generally a global gauge potential. So the gauge potentials are more subtle than just potential forms. They're actually forms like A or C3 here on each chart together with further information, gauge transformation, gluing data on double overlaps of these charts, which in one way, like for electromagnetism, this is another way to speak of all this local transition data is to say, well, the vector potential forms have to be the local incarnations of a connection on a circle principal bundle, right? So this is really what this diagram, what this innocent looking homotopy here encodes. It's something, as the notation next to the arrow meant to indicate, it's something that is locally of the form of a gauge potential as people usually write down for G4 and G7. So it's locally a C3 form and a C6 form, whose differential is locally equal to the restrictions of these things. But there's more data. There's some very subtle transition data that gives these gauge potentials defined on each open or on each chart some global cohomological structure. And that is what can be encoded very neatly in this higher topos theoretic construction shown here. And so I wanted to say, so this was really the second main insight of Dirac. So first of all, in 1930, there is a gauge potential and it's a physically observable thing. But second, and this is kind of in his original language encoded in this notion of Dirac strings, which maybe in modern mathematical language we would say differently. But anyway, this is in what Dirac called the Dirac string. He's really speaking about what mathematicians would call the clutching construction for line bundles on a sphere. So it's a way of encoding the transition data that you need in order to have a Čech co-cycle for your whatever data on the sphere. But in speaking about this Dirac string, at least in hindsight, Dirac is observing that there is global topological structure in how these gauge potentials glue on charts. And that is where the degree 2 cohomology charge lives. That is sort of the actual monopole charge, if you will. And it's that old step from the 1930s that was understood back then, at least in hindsight, by Dirac. I think the first one who actually understood this electromagnetic situation in modern language is maybe Orlando Alvarez in the 80s, who has articles on Čech cohomology and Dirac charge quantization. He phrases these things in the modern language that I'm kind of alluding to here. Anyway, so that insight from back then has never really been much adopted to all these fancy higher gauge theories that appear, particularly in supergravity, where one must ask exactly the same question. What is it that really defines the full global field content? It's the gauge potentials, yes, but furthermore, some topological data gluing this together.
Yes.
And so with this category theoretic language, it's kind of natural. So this is what I'm showing is really the content of this book we wrote, the character map in non-abelian cohomology. It's clear which problem one has to solve. One needs to fill these diagrams, and then one can see what are the choices that one has to make to define a global completion. And I think that's an interesting and underappreciated aspect that actually to fully define just 11-dimensional supergravity, not just even talking about any other fancy stuff like quantization or other lifts, it actually requires more data than is usually considered.
So what does Ed Witten think about this?
Well, I don't know.
Well, he hasn't written much about M-theory in the past few years. It doesn't seem like many people are working on M-theory.
No, absolutely. Yeah, absolutely. There has not been much at all. No, that's right. Yeah.
Why do you think that is?
Yeah. Okay. Let me come to that. Let me say one thing. There has been a surprising and pleasant revival, though, of interest in the matrix models just in the last months, actually.
Yes.
Right. Remember, one of the candidates for defining at least some corners of M theory was the BFSS matrix model, and it already had this type 2B cousin, the IKKT matrix model. And that was always kind of more enigmatic in a way because where the BFSS matrix model reduced all of M theory to kind of the quantum mechanics, right, in zero space and one-time dimensions of these matrices, in the IKKT model it's actually reduced to zero dimensions. Somehow, in some sense, the IKKT matrix model is matrix mechanics on a point. And that has received, so in some sense, it looks a bit deeper or more interesting. And that has received a surprising amount of attention just lately. And I guess there's some claims that I guess the Japanese group is claiming that computer simulation shows that there are spontaneous compactifications to 4 dimensions, somehow seen by numerical computation in these matrix models. I don't know if that has been checked. But yeah, so this is what people have been playing with. And now to come to your question, like why is there no further progress? So I think, I suspect part of the problem is what we alluded to at the very beginning, that it's not actually clear, or it was not actually clear where even to look. Like, how do you go about as a traditional physicist to find M theory? Well, the only thing you can really do is you can write down a Lagrangian, right? That's how people build new theories. You write a new Lagrangian. But the Lagrangian here is sort of already known. It's 11 supergravity with higher curvature correction. So that alone cannot be it. There's something else that is actually needed. The question is actually somehow deeper. What else? How else, besides writing down a Lagrangian, can we actually do to construct a non-perturbative theory? And observe, I never wrote down a Lagrangian here. The equations of motion of supergravity just came to us actually differently. But since we're talking about these things now, how about, and since energy becomes an issue, how about I jump just now to the outlook, because that maybe addresses what I designated as the outlook here. So let's see, what am I saying here? So I would say that there's a grand open problem in contemporary theoretical physics, which is really the non-perturbative aspects of quantum systems. And in this diagram here on the right, I'm showing just how enormous actually the uncharted territory is. If we remember that doing perturbation theory really means we're in an infinitesimal neighborhood, since we're just looking at formal power series, of the point in field space that is kind of around the free and classical fields. Perturbation theory means to behave just infinitesimally in both the coupling constant and the Planck constant. So this huge realm of non-perturbative physics that has remained pretty much uncharted theoretically, but which is deeply known to be crucially relevant in physics. Like the problem that we don't understand this here, like analytically, apart from computer simulation, is really what haunts particle physics, in that whenever QCD at non-extreme temperatures plays any role, any hadronic contributions can never really be fully computed with perturbation theory. Nobody really knows what's going on there. And it leads to huge issues in all these discussions of whether or not people see a new effect beyond the standard model or not. These anomalies, they keep usually growing until somebody finally cranks up their lattice gauge theory computer and does the computation, which cannot otherwise be done. So this is a big issue. And then currently also in condensed matter theory, where all the interest is now on strongly coupled and correlated systems, again, the same problem arises, that there's no actual fundamental theory for these. For instance, effects like the fractional quantum Hall effect or similar topologically ordered systems are seen in the lab, but there's no actual derivation of their description from first principles. The existing theories for, say, the fractional quantum Hall effect are ad hoc effective theories that are made up on the spot. Of course, in a very clever fashion, and there's nothing wrong with it, but it's not derived from fundamental physics since this non-perturbative theory is not known. And now it's interesting to note that the history of this problem has kind of an interesting ironic turn to it. So let's look back. So what happened in the past? So way back in, what is it, the 50s or something? Or maybe the 70s, people thought about this, started thinking hard about this problem of non-perturbative QCD, and there's very good arguments, of course, no real proof that in the confined regime, QCD must somehow be controlled by the flux tubes that are thought to emerge between oppositely charged quarks, confining them, holding them together. So the idea back then was that, well, since that is the most important phenomenological effect in the confined, hence in the non-perturbative regime, so let's probably the flux tubes are the actual degrees of freedom to be discussed for non-perturbative QCD. This is really where the idea of strings originates from, that you say, well, okay, let's write down action functionals and dynamics for these strings that are the flux tubes. And then comes this computation, which is really still at the heart of much of the, how should one say, of the derangement of the field. So you write down the quantum dynamics of these flux tubes and find that they only make sense in more than 4 dimensions. 5, maybe if you use Liouville theory, or if you use critical strings, then even 10 or 26. So this is where strings seem to get really weird back then, where people didn't know what to make of it. The origin of the hypothesis of strings was very much rooted exactly in experiment. Understand the last, if you will, the big but last remaining gap of the standard model, the actual non-perturbative sector. So you introduce the strings, and now suddenly you're faced with this new situation that you have this high-dimensional space, which eventually, in fact, Polyakov said this right away at the beginning, but it was eventually realized to have to be understood as kind of a high-dimensional unobserved bulk space-time that hosts the actual observed space-time, which sits in it in the form of a brane, where the quarks kind of sit on the brane, and the strings in their need for a higher dimensional bulk may have the endpoints attached to these quarks, but may otherwise probe this bulk. And then, of course, well, you know the story. Then holography develops, and there is a form of it called holographic QCD now, where you ask, well, can we build a string model that holographically describes actual QCD, and a whole lot of numbers can actually be crunched out there. There's actually quantitative experimental comparisons there. But kind of the irony of this whole project is that, of course, the strings were introduced in order to capture the non-perturbative aspect of QCD, but the strings now were themselves only understood perturbatively in perturbative string theory. The big difference is that, as opposed to the original field theory, its reformulation in terms of these strings now comes with lots of hints, or a whole network of hints of what the non-perturbative completion would be. This is really what the second superstring revolution is about, the observation that if you have strings, then there's branes which have non-perturbative couplings and so forth. And so this working title M theory really refers to the question of how to make sense of strings non-perturbatively, but if we remember at this point, then in some sense historically, that is really the answer to how do quarks behave non-perturbatively. Then at least in this rough outline, M theory reappears, at least as the possible ultimate answer to how to actually define, construct non-perturbative QFT. And so the question then is, how do we even go about formulating M theory? Like, do we write on a Lagrangian, or is it just another matrix model? And I would argue that, and now I'm coming to an end, I would argue that, language has been missing here. We're looking for a new kind of theory, and so some of the old starting points maybe need to be not revised, but replaced by something that goes deeper. And I guess one can see a hint of this in this famous quote by Witten, which he himself attributes to Amartya, about how string theory is so perplexing because it seems to need math that would only be developed in the following centuries to find its true formulation. And maybe, I very much agree with this sentiment, and I guess what I've been showing here is kind of suggestive of possibly being parts of an answer in this direction.
Well, that's a beautiful talk, and I appreciate you premiering it here on this channel. I'd like to also wrap it up with a quote from you from that same philosophical stack exchange. In fundamental physics, it is, or at least was in the 1990s, common to declare that with a certain awe and pride that quantum gravity, non-perturbative string theory, and the like will force us to do things like, quote-unquote, radically rethink the foundations of reality or something similar. Unfortunately, that rethinking has mostly been what I think is a fair bit naive. One can't just talk about it. It needs to have both a technical understanding of the core mathematics up to that very edge, where we do understand the formal laws of nature, and a trained, profound philosophical mind who can stand at this cliff stare into the misty clouds beyond, and suggest directions along which further solid ground of formalism may be found. Once it is found true, then the philosopher should probably step back and watch those mathematicians and physicists build a tar road over it and then run heavy trucks back and forth into uncharted territories. But before that is possible, the new stable ground has to be found first. Urs, thank you so much for coming on. I appreciate you spending three hours with me.
Thank you, Curt, for inviting me and for doing this. I appreciate it. That was a fun experience.
I've received several messages, emails, and comments from professors saying that they recommend theories of everything to their students, and that's fantastic. If you're a professor or a lecturer and there's a particular standout episode that your students can benefit from, please do share. And as always, feel free to contact me. New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, "Hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts?" While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook, or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, Toll listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Curt Jaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.